So we'll be discussing constraint motion today. So I'll be telling you various methods of solving, and the different approaches may appeal to different people. So whatever you find easiest, you can use that. So what's a constraint motion? In a constraint motion, one body is somehow linked to the other body. Say this body 1 linked to body 2. So if one body moves, like if I move 1 by a certain amount x this side, then this 2 is bound to move up by the same amount x. If this string, black string, doesn't extend, it maintains the same length. So whatever is the length initially, say A plus the curved side plus B, so that much length remains same. So if it moves x this side, then this body has to go up by x. So here the mass of the body, whether this is 1 kg and this is 100 kgs or whatever, the mass of the body doesn't matter. It is the movement. If this body went down by say 2 centimeters, this body has to go on the other side by 2 centimeters. Plus we can see other constraints are also present. There is a ground. It cannot go into the ground. This one is going to go vertical because of gravity being vertical. So those constraints are there. So we are going to deal with questions where bodies are going straight up and down and horizontal. Then some questions where the bodies are going, where the rope in fact is going in an inclined direction. Questions where you have the rope going at an angle, and then some questions where you have one body on top of the other body. So particularly like a wedge. Whatever. So these are on top of the other body. So we'll be discussing all these questions and various methods to approach them. So let's start with a very simple example first. Now let's take a very simple example of two masses overhanging from two sides of a pulley, and we have to find out that what's the ratio of the movement of this is to this. That means what is the ratio of the displacement of body 1, say moves by x, and this goes down by y. So what's the ratio of x is to y? Or say it had a velocity of v1, and then this one is say v2, or the ratio of acceleration a1 and a2. So whatever we find, whether we are going to find the ratio of the displacement or the velocity or the acceleration, the ratio is going to be the same, meaning to say x is to y is going to be your v1 is to v2 is going to be your a1 is to a2. The reason is in a certain amount of time, the distance covered by this will give you the velocity of the first mass, and in the same amount of time the distance covered by this will be y. So the speed would be given by x by a certain time divided by y by the same time. The reason is that if the body covers this distance x in a certain time, say t, then this body is going to go down by y in the same time t. So the velocity of this body will be x by t, and that the velocity of this body will be y by the same amount of time t. So if you want to go into instantaneous velocities and not average velocities, still the story will be same. You'll have dx by dt. We'll be studying the ratio of dx by dt, which is your v1, with dy by dt, which is your v2. Now the ratio of dx is to dy is going to tell you the ratio of the velocities also, and dx is a small movement of body 1x, and dy is a small movement of body 2y. So the ratio of dx and dy is going to be same as the ratio of the mega distance moved, which is your x, and this is your y, because all these dx added is ultimately going to be your x, and all the dy's added is going to be your y. So it moves say a 0.01 millimeters up, and this one goes, like in this case it goes 0.01 millimeter down. Then every 0.1 millimeter up, it will create a 0.1 millimeter downward movement, and you add up all, and it becomes ultimately a 1 centimeter up, then this would be 1 centimeter down. So your dx is to dy ratio is same as your x is to y ratio, hence your velocity ratio is going to be same, and the speed gained, this is your v1, this is your v2, that ratio is going to be same. dv1 by dt is the ratio of your accelerations, that's your a1 is to a2, is again v1 is to v2 is same, so we have differentiated that, hence a1 is to a2 is also going to be the same. So sometimes they'll be giving you acceleration of 1 and they'll ask you acceleration of this, sometimes they'll give you velocity of 1 and ask you the velocity of this, sometimes they'll give you displacement and you have to find the displacement of this. All these cases the same constraint will be there. Now how to figure out that if it moves x up, then what would be this y quantity, how much will that be? Now to figure out that, one is just analyze the situation and have a physics brain working over here. If it goes by x up and the total length of the string can't change, then this string has to go down by y. So we can represent this in many formats. So one is a more mathematical one. We'll not prefer this later on. We'll do by intuition more than what I'm going to show you right now. We'll just see the total length of the string. So say this part length was equal to A, this part length was your B, and say you'll count the curve length also, which is actually not required because that curve length is going to come again. The part of the string will always be on the pulley, that much part. Say that is C. So what's the total length of the string? The length of the string L is equal to A plus B plus C. Now the length of the string is never going to change. Now we'll draw the new situation now. Let me clear this off first. Now what I'll do is I'll draw the new situation over here on the same diagram and not separately. So that's your new position of the blocks, and this orange string is now representing how they are held together. So what was your black string earlier is now your orange string. So we are just going to measure the length of the orange string. Now mind you, we know how much will be the movement and all, but still we'll say that this block from this where it held the block to where it is holding now, that distance moved. So this one has moved up by x, and 2 again from where it was holding the block to where it is holding the block, this block 2 has moved down by say y. Now we are going to count the total length of the string again. Now the total length of the string, now it's an orange string, so I'll write in orange. I hope it is visible. So total length of the string now will be this orange section. So how much is that? How much is this much? So this part was A. So this is x less. So this part must be A minus x. So that's this section. What about this section? What about this length? So from here to here was your B. Now you have y more. So this becomes B plus y. And this part remains the same. So need not count it in the initial length also, because this will always remain the same. So what you get is A minus x plus C remains as C, and you'll have this part as B plus y. And this length and the earlier length was the same length, so we can equate the two equations, and what we get is A's will get cancelled, your B's will get cancelled, your C's will get cancelled, and ultimately what we get is 0 is equal to minus x plus y. In other terms, your y is equal to x. So that we already knew just by inspecting the situation. But this is what you are doing actually. You are ensuring that the whole string length is the same. So in this very simple question, you need not do it. And then in this simple question also, measuring all the lengths, all the parts was little cumbersome. It was tedious. So what we could have done is, we could have, I'll redraw this. Yeah, so instead of measuring all the parts fully, that is a plus b plus c or a minus x plus c plus b minus y, what we can inspect is only the parts of the length of the string which is getting reduced and extended. So this part of the length got reduced by x, this part of the length got extended by y. The length of the string, we will imagine it is from the point on the pulley till wherever the block ends. Now the block is ending over here, and this block is ending over here. So what we see is that this part of the length got reduced by x, and we'll write a minus x to the total length, which we are not mentioning, by the way. And this part of the length got increased by y, so we'll mention it as plus y to the total length. So total length minus x plus y remains as the total length. Total length minus x plus y remains as the total length. So this total length need not be mentioned all the time, and we can write minus x plus y is equal to 0. The total length and total length is going to cancel off. So what we are going to get is y is equal to x. Now this is much faster than mentioning all the parts, and maybe more simple and lesser chance of you getting into an error. But you have to carefully inspect all the lengths of the string which can reduce, and this will work on a single string. If you have 2-3 strings attached, it's not the same string which is going along, then this concept you'll apply on each string separately. You can't apply it on all the strings. So this becomes a method of doing, but the preferred method over here was just inspecting. If you are too much into maths, you can write the length reduced and the length increased. If you have to be very, very sure of what is happening, you can count on all the lengths, but this diagram may become messy if there are more pulleys and blocks involved, which will eventually be the case. So let us study another case where you have a movable pulley. So here I am not making a block just to make the thing simple. So what we are going to do is, we are going to study the movement of this point 2 and the movement of point 1. So suppose we take it up by x, then how much is this going to move? So that is what we are going to study. So before I do it for you, just give it a go. You can redraw this diagram with the new position of the pulley, which is say here, and then the new position of the points, and do what has been told earlier to you. So now how to deal with it? So what do you expect? If I take this point up by x, will it going to go up by x or not? Your physics brain is working over here. You would say that no, it is not going to go up by x, it is going to go up by less amount. Because as you pull this up, this thing is going to rotate and go up, and the same movement is not provided to this. Now that is by intuition, and then you'll analyze that what is happening over here. So now the best is to move this movable pulley in a direction which is going to loosen up all the strings. So what you can imagine is, you have laid all this down on a table and there's no gravity and all. All the strings have to be tight. So if you lay it down on a table and move the pulley up, so we'll concentrate on the center point of the pulley. So it was here earlier, now it is here. So you have moved the pulley up by, say, since I said x for that, let me write it as a. So if you have moved the pulley up by a, what has happened now? So we'll analyze what has happened now. The thing is, this body 1 was directly attached to the center of the pulley. So if the center of the pulley goes up by a, then this also will go up by a. So this movement is straight. It's a straight constraint. It is directly attached to the body. So whatever is the movement of the pulley is the movement of the body. So the body goes up by a. Now what happens to the string? What we see is, this was your string. Earlier we have not moved this part, we have laid it down on the ground, and we are just seeing that what is happening in the new position. Your body 1 has gone up by A amount. So now it is up to us to pull this part of the string to make it again tight on the pulley. Now this part is overhanging. So when it becomes tight on the pulley, then whatever was the curved part will again come back on the curve. What was the loose string which was hanging is so much and so much. So you have loose string this side as well as this side which is overhanging. That's your loose string. This is the loose string which is overhanging, and this is going to become tight. So how much you have to pull this side so that this loose string and this loose string is tightened again. So how much is that amount? This loose string is A here and A here. So what you have to pull up by is 2A. You have to pull this point up by 2A so that the loose string again becomes tight. So that is how you do by inspection. You move the movable pulley in a way such that the strings become loose, and then you tighten the string with your own hand. While you are moving the movable pulley, the things which will not move automatically, like this body and all, will move automatically. The things which will not move, it is not bound to move automatically, just stay them put at where they were, and just move the movable pulley, see where the strings have gone loose, and then tighten those strings. Pull one by one and tighten those strings. So if you pull this by 2A, then your A and A is going to get, the loose string A and A is again going to become tight, and eventually the body is over here, 2A. So going back to the original question, if this has moved by X and this has moved by Y, then the relation is X is equal to twice of Y. X is your 2A and Y was your A. So whichever movement is asked, whether the body was asked to be pulled down or pulled up, it will not matter. If the body had gone down by A amount, this point would have gone down by 2A amount. So in the initial question, whether it is that the body is going down or going up, you are going to work to make the strings loose, because that comes more easily to the mind. If the strings are loose, then you are able to understand the situation, analyze the situation better. So eventually this question would have been something like this. So we have analyzed the movement of this point. So when this is going up by A, this point is going up by 2A. This is a fixed pulley. So if this point goes up by 2A, a point over here is going to go down by 2A. Eventually the body is going to go down by 2A. So what we are seeing is, in a fixed pulley case, as the earlier case, the movement on one side is equal to the movement on the other side. But when there is a movable pulley, it's dicey. You have to see what is actually happening. So generally, if it is one movable pulley, you will have a factor of 2. Like if the movable pulley moves by X, then the point on the other side is going to move by 2X, provided this side was fixed. You can think of a knot tied on this, and think what happens to the knot while you are pulling this point up. What happens to the knot? The knot remains over there, because this length remains the same. This point is attached to the wall, so the knot is also going to remain there. So whatever part of the string you watch over here is going to remain there itself. And all these strings which have to be pulled up has to be pulled up on the same side. So if I had to solve this question, my preferred method over here would be analysis. I will identify where the movable pulley is. I will lay everything on the ground such that there is no effect of gravity or anything. I know all the strings are going to be tight. I am going to move the movable pulley in a way, in a direction which loosens the strings, and I am going to tighten the string again. So when I move the movable pulley up by X, I get X and X, 2X loose string. So to tighten the 2X loose strings, I have to pull this thing down by 2X so that the whole loose string, this blue loose string, gets tightened, and this loose string comes back on that thing. So that is my analysis way. That's the preferred way for me over here. The other way would be, as I have said earlier, this is one string. We can just watch on the lengths of the string. So one way is mark all the lengths from the ceiling to the pulley, the initial length, and then from here to there. Okay, I'll quickly mark it, but I'm not going to do this way in any given case. I'm not going to do this way what I'm going to show you right now in any given case, but still, to get a feel of the whole length of the string and everything and how it is going, I'm just going to mark it. Say this part is A, this part is B, and this part is C, and the lengths over the pulley is same. So this is the orange string which I'm counting on. Later on, the string is this black one. Pulley has gone up, gone up, gone up. So the body has come up. This string would have gone down. So this is the black situation is the later on situation. Now, if this pulley has gone up by X and this thing has gone down by Y, so I'll just write the total length again. So the total length on this side would be A minus X. A was the initial length, but it has gone up. So this is your length now, which is your A minus X. What about this? This was your B. It has gone up over here. So this length becomes B minus X. So this length is your B minus X. And what about this side? So we'll not call it as 2x yet because we have not found out what's the relation. So we'll call this side as this extra length is your Y over here. This was your C. So this is your C plus Y. So that's your total length of the string. And in the blue case or in the orange case, in fact, earlier the total length of the string was A plus B plus C. So you can rewind and watch before I had drawn this black rope. The length of the string was A plus B plus C. So it must be equal to A plus B plus C. So what we see over here is A, B and C gets cancelled. You get minus 2x plus y is equal to 0 or y is equal to 2x. So here marking the whole length was not necessary. So improvised version of the same thing would be, again I'll redraw for you. One thing you may notice, I'm just concentrating on the movement of the pulley. I'm not talking about this mass moving, because I know how much ever this pulley moves, that mass moves that much. So you may look out for such setups where the mass is attached to the center of the pulley. So how much ever the pulley moves, that much is how much will the mass move. Now, if this pulley has gone up by X amount and this has gone down, this body has gone down by Y amount, then what can I say about this section of the length? This section of the length has reduced this section of the length. One coming from the pulley to the attached point. This section would have reduced by X. So reduced by X, whatever minus X. So that whatever, by the way, was A. And the here whatever was your B and the here whatever was your C. So whatever minus X and whatever was the length earlier, that length has also reduced by X. The top point has remained where it was, but the bottom point has come up by X in the new situation. So minus X. And here, this section of the rope, this point is here itself, and this would have gone down by Y. So whatever length, that was a C plus Y. So this is what we are talking, minus X plus Y. So the total reduced length must be the total increased length. So if we write like this, so it is equal to 0, what we get is Y is equal to 2X. So I think this is much faster than drawing all the lengths. In fact, in many a case, you need not draw the pulley again. So one is intuition. I'll prefer intuition over here. I take the pulley up by X. I get a loose string over here. Of X and X 2X. So I have to tighten this part by 2X to make the string tight again. Why am I saying that I prefer this method? Because I'm more closer to physics when I'm thinking of all these things. When I just write minus X plus Y and all, that time I am more into mathematics, but I'm not getting into the feel of the question. So I would prefer the first method. Now, so my methods were, one is analyze. Method 2 is, so I've listed down 2 methods. I'll do one more method for this setup. So first method was analyze, and that is by inspection you find out. I move the movable pulley one. And the next method is you write the increase and decrease in the length of each section of the string and equate it to 0. How much each section of the string, so these were 3 sections in the string. 1, 2 and 3. This section has decreased by how much, this section has decreased by how much, and this section has increased by how much. So that was your decrease, decrease and increase, and equate it to 0, and you'll get the constraint relation between the movement of the two ends over here, provided all the strings are tight. So one more method over here is related to work. So that will require a bit of knowledge of forces and work. So anyhow, I guess you would be knowing that much. So let me show you over here. This is a clean area. Whether this was a body or this was a point which I was going to pull down, and this point is going to go up, or this is a point which I'm going to, in this case it is made like Y pull down. So this is going up by Y. So if I had put a force on this, say I had put F force on this and has gone down by Y amount. So what is the work input by me? How much I have done work on this by this force? The force has done a work of F into Y. Now in any machine, whatever is the input work in has to be equal to work out, or input work is greater than work out. Input work is greater than equal to work output. Output work cannot exceed the input work. So efficiency can't go more than 100%. Now if I have to find the relation between the movement of the two bodies, then whether this pulley was having a lot of friction, whether it was an ideal situation or not, it was creaking when I am moving it, when I move it, but ultimately when I move this Y down, it has to go the same X amount up, whether it was having a lot of friction over here, or there was no friction. So if I have managed to move it Y down, this has to go X, which is equal to Y, up in this case, if I have managed to move it Y down, and this string is not extending, it is inextensible. So the point is, whether the pulley was ideal or not, I can change the situation to ideal situation, and I'll say if it was ideal pulley, and if it was ideal pulley, then there is no loss of work in the frictions, in overcoming the friction here, in the friction over there, and say the string was having no weight, so there is no loss of work anywhere. So the only work which is getting input and output is these endpoints. So whatever I have inputted the work, that much output must be there. Now we also know by the third law of motion that if I pull a string down by F, the string is going to pull me up by the same amount F. So your T is equal to F. If the string is massless, then this T is going to get transmitted with the same value. This T is not going to reduce. So what I'm doing is I'm just changing the whole situation to an ideal situation. Now here in these cases, when I said it, I never mentioned that these are ideal pulleys, means having no weight and there's no friction and all. There could have been friction, there could have been weight of the pulley, but still whatever has been discussed earlier remains the same. The only thing is the string was not extensible. The string could have got a mass also, but it was not extensible. Now if I have to do it by work, I just imagine that everything is ideal. So whatever is the work input is the work output. So what is the work input over here? F into Y. That's your work input, F into Y. What's the work output? So what we see is the tension has done the work over here. Tension into Y or X is the work output. That was your X. So the work output is tension into X. They would be equal if it is ideal situation. And by third law of motion, F is equal to T. F is equal to T. So your F and T cancels. What you get is Y is equal to X. So that is obviously much ado about nothing. This question is having no great analysis is required to figure out that if this goes up by X, this is going to go down by Y. But what I'm trying to emphasize over here is we can use work to get the restraint in this situation and all these situations. So what we have done for ICSE guys would be knowing it. What we have done is we have taken an efficiency case of 100%, and then we know that velocity ratio is going to be equal to mechanical advantage. Velocity ratio is movement of the effort, distance moved by the effort divided by distance moved by the load is your velocity ratio, and mechanical advantage is your load divided by how much effort you apply. So effort is where you are putting in the work, E times dE. This is the work input, and load times dL is the work out. So in an ideal situation of 100% efficiency, VR is equal to MA. So that is what we are going to analyze. So whether this machine was ideal or not, it was all greased up or not, we know that the constraints are going to remain same. So even if the machine was not ideal, we make it ideal. We make it ideal means we put all the pulley weights and everything as 1 and no friction, and then do it through work. So if I do this question through work, method number 3, on this question if I apply work, let's see what happens. You also try to write an equation. So where are the input ends and the output ends? You can consider any one as the input work end and the output work end. So I'll tell you one thing to do where you don't have to bother about the input and output work end. So here F is down and the body goes down. So we said a work of Fy, positive Fy is done. Here the tension is up and the body goes up. So a positive work of Tx was done. I'll just clear this area. So there was a positive work of F into Y because the force direction was downwards and the movement direction was downward. And there was a positive work of T into X because your X was upwards and the force was also upwards. The tension was upwards. Now if I see what is the work done by this tension on this body or on this point, then what is the work done? Tension is upwards, but the point is going downwards by Y. So what is the work done by the tension? The work done by this tension is T into Y, but negative because tension was upwards, but the thing has gone downwards. So T into Y negative is the tension, is the work done by the tension. The work done by the tension all over. What's the work done by the tension over here? T into no movement of this point, T into no movement of that point. What is the work done by the tension over here? Work done by the tension over here is T into X. So if we add up all the work done by all the tensions, we add up all the work done by the tensions, we get the total work done by tension is 0. So one explanation can be this. Your F and T were vectorly opposite. Your F magnitude was equal to T magnitude. So what I said over here, you can apply that and think of why total work done by tension will be equal to 0. You can say that the tension is an internal force. Internal force acts on both ends of the string. The tension acts, it pulls both the ends of the any section of the string, as you see drawn over here also. So that's the internal force. Now if this string is going to be tight all the time, then if this part moves this side by x, then that part is going to move that side by x. So the work done over here will be a positive Tx because T in the direction of the movement, but here the work done will be negative Tx because T is this way while the movement is that way. So the movement has to be that way because the string is tight. So if the string is tight, we can analyze any two ends of the string and say that the work done on one side is equal and opposite to the work done on the other side. So positive Tx this side and negative Tx this side. So total work done is always going to be 0. So this becomes another method to do this question. So that's all theory. We'll apply that method over here and then we'll understand. Remember, take it as ideal. Even if I give you weight of pulley and all, make it as 0 mass pulley and do it. So give yourself a minute and do it while I redraw the question. So that's your question. Let me draw the tensions in front of you. Tensions in any section of the string, pulls both the ends of the string. So the tension over here, it's pulling the wall by say T amount. Other end is pulling the pulley up by T amount. This section again will pull both the ends. It's the same string which is going, so TT. This section again will pull both the ends, TT. Now if this pulley is massless, then what we can say is this T in this part of the string or this section is equal to the tension in this section is 2T. Now why do we say that? Say it was T dash. We make the free body diagram of the pulley. Now this is off the topic, but I'm just making it over here because I've seen students making mistake over here. So two tensions were pulling it up and the tension down was T dash, and suppose we don't agree that it is twice of T. We have made a free body diagram of this. We'll write an equation for movement of this. Say the pulley was going up with a certain acceleration A. If there's a residual force on it, there's a certain acceleration produced, which is say A. So if the body is going up, then what we can say is all upward force T plus T minus the downward force T dash must be the mass of the pulley into acceleration of the pulley. If this mass is considered to be 0, what we can write is 2T minus T dash is equal to 0. Hence we say take T dash as 2T. So this T dash becomes 2T only if the mass of the pulley is 0. So now what I said, even if there is mass, the constraints would be same, but you consider the mass to be 0. So therefore I was emphasizing on that. Now these are the two ends where you can write the work, and all other ends you may ignore writing, because whatever tension is pulling whatever thing, if you considering any other concept not applicable over here. So what we are going to concentrate, as explained earlier, is the input and the output point. So here if I'm going to pull it down, this is going to go up. So the input work will be my force downwards into the movement down. But in that case I have to write input is equal to output. The other format of the same thing is the total work done by tension is equal to 0. So we'll concentrate on the work done by tension at the input point and the output point, not the work done by me, not the input work done, but the work done by tension at the input point. So let's see what were we doing earlier, that this point is going up. Okay, so this goes up by say X amount and this comes down by say Y amount. And we don't know the relation yet between your X and Y. So what we can write is the work done by tension over here is 2T. 2T was upwards on that point and it has gone upwards. So it is a positive 2T. The work done over here by the tension on this point is, the tension was upward but the point went down by Y. So it is minus Ty. And the net work done has to be 0. The T's get cancelled and what we get is 2x is equal to y. So that's again the same relation what we were getting earlier. Here I'd called this as y, so that was the other way around. Here I'm calling this as x and this as y. So this has gone down twice the amount of how much it has come up. So again a very useful way, but not required in this particular case. But many cases you'll find this work done method quite useful. So I'll write down our method 3. Total work done by tension is 0. So going by these methods you'll be able to pretty much solve most of the questions. So even if you are getting it through the mathematical methods like 2 and 3, try to analyze how the things are moving and verify in your head that whatever you are getting through the method is aligned to what you have analyzed. So let us take up some problems of more worth now. Now before we go on to solve a question, let us just add one more option to our preferred methods, one more tool in our kitty. Particularly helpful when there are more than two bodies moving. So say this looks very odd, so I'll just draw a point over here. Say this is going up with a certain velocity. This point is 1, this point is 2, this point is 3. So this is going up with V1. This is going say up with V3 and this is going up with V2. Say all of them are going up with a certain velocity. It could have been going down or any other way. Now these are the velocities with respect to ground. V1 with respect to ground, V2 with respect to ground, V3 with respect to ground. But we very well know that there is a relation between V2 and V3, particularly when we see with respect to the pulley. With respect to the pulley, how much ever it has come up, that much it must be going down. So the velocity with respect to the pulley was, suppose u up over here, then with respect to the pulley it is u down this side. So velocity of 2 with respect to the pulley is equal to velocity of 3 with respect to the pulley. So this is, one is upwards and one is downwards. So one is negative of the other. What I'm planning is to use our known equations in relative motion over here. What do we write velocity of 2 with respect to the pulley as? We write velocity of 2 with respect to the pulley as V2 minus velocity of the pulley. So that V1 is your velocity of the pulley. So I'll rather write VP over there. Is equal to negative of velocity of 3 with respect to the pulley. Velocity of 3 with respect to the pulley is V3 minus V pulley again. So what do we get over here? What we get over here is V2 minus Vp is equal to minus V3 plus Vp. If we rearrange and write, we'll get velocity of pulley is equal to V2 plus V3 divided by 2. This goes on the other side, that goes on this side. So this is an important relation. What we are getting over here is, and since all of them are in straight lines, so this is a vector equation. So I've taken everything up, up, up. So V2 up, V3 up, by 2 is Vp. So this was, say, going with 2 meter per second up, and this was going with 4 meter per second up. Then the pulley must be going up with 3 meter per second. If this was going up with, say, 2 meter per second, and this body was also going up with 2 meter per second, meaning to say both were, this length of the string is not increasing and both are going up with the same velocity, then the pulley must be going up with the same velocity too. And there's no movement, there's no relative movement between these two parts. So if this is 2, this is 2, this must be 2. So that is what our equation gives, 2 plus 2 by 2, which is 2. If this was 4 and this was 2, then the pulley must be going up with some average speed of 4 and 2, which is 3. The pulley must be going up. Then only it can accommodate this also going up, that also going up, with the string being tight. So for our convenience, I have written everything in one direction. So let us just apply this in one or two more situations. If I say this point is going up by 2 meter per second, this point is going down with 3 meter per second, find the velocity of this point. So this point is going which way, up or down, and with what speed? So we'll simply apply the formula over here and we'll check it through our analysis thing. So what we write is the pulley, say upward, is all positive. So because this is a vector equation, so we'll have to take positives and negatives. So remember, all of this is happening in a vertical line, in the same line. So it is quite, this formula becomes quite easy to apply, only plus and minus here and there. So 2, say upward, so velocity of the pulley is 2. Velocity of this body 2 is downwards. This was up, which was considered as positive, so down is negative, so downward will be minus 3 plus whatever velocity we have to find. If it comes positive, then it is upwards. If it comes negative, then it is downwards, divided by 2. Before calculation and before going to look into the math, what do you think? This body will be going up or going down? Analyze a bit and tell me. So to analyze, what I do is I make things stationary. If the pulley was stationary and this body is going down with 3, then it was going up with 3. So give me a big hint that it might be going up with 3. And plus this 3 is a larger number than 2, then maybe the 2 is, whichever way it affects, it is not going to affect the 3. So it gives me a hint it must be going up. Anyways, if this is stationary, this is going down with 3, it goes up with 3. If this was stationary, this block was stationary, and the pulley is going up with 2, what will happen to this? If this block was stationary and the pulley is going up with 2, this will still go up. So both the movements, the body going up as well as this thing going down, causes this thing to go up. So my guess is it is going to go up more than 3. I'm not even guessing, I'm not only guessing that it is going to go up, I'm guessing that the value is going to come more than 3, because if this was not moving, if the pulley was not moving, this alone 3 movement down would have caused a 3 movement up. And the pulley moving up is going to make it move up even more. If the pulley had gone down, then the string over here would have become slack and this would have gone down. Then it could have been debated what is happening. So over here, what we calculate and what we see is, you'll have your V is equal to 4 plus 3, which is 7, which is what we guessed. So our analytical mind is saying, yeah, we should get a big number, we should get an upward big number. So that is your 7 meter per second. So take a pause and analyze this thing. Why we should get a big number upwards. Don't concentrate on just applying the formula. Concentrate, consciously get yourself involved with how the bodies are moving. Analyze what is happening, and you'll be more close to solving questions if you have that kind of analysis. Say the pulley was going down, and say it was going down with 2 itself. So I'll just change the question. It is going down with 2. So this over here becomes minus 2. So I'll redo the question this side. So the pulley is going down this time, minus 2 is equal to minus 3. This is going down plus V by 2. Now my guess is this going down is going to make this go down. This body going down is going to make this go up. Now who is going to win? My guess is the pulley downward movement, which is going to make this which will make this going down, is going to win over this downward movement, which is going to make the body go up. Now why that? Because a certain movement in the pulley, say x in the pulley, gives you a movement of 2x over here had this not been moving. If this is stationary, again I'll apply the same principle. I'll make this stationary and just move this and see. So if it goes down with 2, it is going to make it go down with 4. Now since it has gone down with 4, this pulley have to make it go down with 3, so it is going to pull it up by 3 back, because that's a direct link. So 4 minus 3, I should get it as 1. Let's see what we get. So what we get over here is 2 into 2 is minus 4 over there, and 4 comes this side. So it is 1. So we get, in mathematically we get V is equal to minus 1. So upward was our positive direction, downward is negative direction. So we get 1 downwards, 1 meter per second downwards. So that is what we have done through analysis also. So this formula is a safe formula, but do try to analyze also. So I'll just repeat the analysis over here. Pulley going down with 2, this going down with 3. Now even if it is accelerations, the ratios will be same. Even if it is displacement, the ratio will be same. So it is 2 meter per second in this case, that's the velocity, and this velocity is 3. So I had guessed that this will be going down. The reason was, if I don't make this body move and I make this body stay put over there, and I move the pulley down with a certain amount, it goes down with say 2. So this body remaining over there will make the string tight by moving this down by 2 plus 2, which is 4. If this is x and x, this would be 2x. It has to go down by 2x because he had caused a loose string over here of x and x. Now once the body is over here, I realize the pulley has made its movement. The pulley is down by 2. The pulley is over here now. So we are done with its movement. In 1 second it is down over here. But then they said that in 1 second this body had to be down by 3. The velocity with respect to ground was 3. So I'll make this go down by 3. If I make this go down by 3, this has to come up by 3. So it has gone down by 4, comes up by 3, goes down by 4. So ultimately it is down by 1. So think over it. So in the analysis part, I forgot to mention over here, if there are too many moving parts, you make them move one by one. So we'll do that. We'll do that when we take up the questions. So this becomes a tool for you. If two things are overhanging a pulley, then we can say velocity of pulley is equal to velocity of, say, body 1 plus velocity of body 2 are the two bodies overhanging the pulley on two sides divided by 2 in a vector situation, in a vector equation. So that's your VP, that's your V1 up and V2 up, all same direction. That's vector in one direction. This is the vector equation. So that becomes a tool for you. You can use this also when required, but don't forget to analyze what is happening. So now let us take up some questions involving pulleys. So after that we'll have what they call as wedge constraints, when one body is on top of the other body. So I put up two situations on the board. Let's analyze this and do. Both are having just two bodies. One moves, the other one is going to move. Later on we'll be doing situations where we have more than 2 bodies, 3 bodies, and even more, so those will be more interesting to do. So here I've made the pulleys not symmetrical deliberately so that you realize what are the factors which are actually having an effect. You can consider whatever radius you want. You can consider this as R, this as 2R, this as a 4R. Then obviously this can be calculated, back calculated. So I'll make it even more, say 5R if required, and try to do this. So I'll give you some time for this. Take your time, take your while and do. By analysis, let us see the first method first. By analysis, it is all flat on the ground, no effect of gravity, nothing. All the wires, all the strings have to be tight. So I can move any one movable pulley and keep the other things still and see how much of the other movable pulley has to be moved so that the strings are tight again. So what do you want to move first? Say this small one is taken up by, so I'll redraw over here, so I'll not mess up the main diagram. By the way, sizes of the pulley is not going to matter. Once we are done with the question, you can analyze on that. If you have any doubt, you can ask me later. So, by the first method, let me move this movable pulley up and not move anything else. So this has gone up. This point has gone up by, say, X amount. So what is created? There is a loose string which is over here, which needs to be tightened. So if this has gone up, everything remains at the place. Then what we can do is either we can pull both the sides or one side. So suppose I pull one side by X. Is it going to make the string tight again? This is a loose string. No, we have to pull one side by 2x. If I pull one side, I have to pull it by 2x, so that I'm holding this side, I'm holding this side, and I'm pulling this by 2x. So the whole thing, this x plus x will get again tightened. So when this is pulled by 2x, how much will this fall? This is going to fall by x only. Why it is going to fall by x? Because a movement of x over here, requires x plus x, 2x extra string. So you have all this 2x goes into this x and that x. All this part is still held and it is remaining over there. The other way of thinking was, when I pull it down by x, then we have x plus x, 2x extra string to be supplied from somewhere. So where can that 2x extra string be supplied? If this goes up by x, again x plus x, 2x extra string it will supply. So what we are noticing over here is the dia of the pulley doesn't matter. This is a big pulley, there's a small pulley, but the movement of both the pulleys were x. So how much ever is the size of the pulley is not mattering, because whatever amount of rope is sticking to the pulley is still sticking to the pulley in later on situation also. And what matters is the side lengths, this and this. So here xx, and there also it is x and x. So the answer is this goes x up, then this goes x down. That is by analysis. If you are able to do that way, well and good. If not, then let us take all the sections, length of each section of the string, and see the increase and decrease and equate it to 0. So we say that body 2 has gone, okay, we were doing it down, so we'll do it down, sorry. Say we have this body 2 going down by y and this body 1 going up by x. So if the body 1 goes up by x and the body 2 goes down by y, and all the strings are tight, So what has happened to this section of the string? We'll take all the sections starting from, say, this section. So what has happened to this section of the string? That section has reduced in length by x amount, so minus x. What has happened to this section of the string? That section has also reduced, the pulley has come over here, the section has reduced by x amount, so minus x again. And this pulley has gone down. So what has happened to this section of the string? This section, it has gone from this point to some point over here. So this has increased. So how much is that? That increase will be plus y. Whatever was the earlier, plus y. Whatever. This was the whatever earlier. And this section has also gone down by y. So that is also plus y. So net decrease is equal to net increase. So decrease has been x and x, and increase has been y and y. So what we get? We get x is equal to y. That is your method 2. Now method 3. Okay, so in method 3, again, let me redraw very fast. So here in method 3 we will see the work done by the tension. So one can be thought of the input place and one third can be thought of as the output spot. So tension here is up, tension here is also up. Say this goes up by x and this goes down by y. So the work done by tension over here is positive, over here it is negative. So how much is the tension? So let us consider this string. So tension in this string is T, 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 T. Any section of the string, it pulls both the ends. So you see, watch carefully. Any section I'm drawing two. I'm not just drawing one tension line. Whenever you draw in a section, draw both. Pull both the ends. Even though the other end may not be required in a particular question, but put a habit of drawing both the ends. That's quite important. So what's the tension over here? 2T. As explained to you earlier, we'll consider the pulley as massless and all. And this is 2T. So downward tension and upward tension. The downward is 2T and upward is 2T here also, because this is up, up. So this down on the pulley is 2T. So this up is 2T. So what we have is the work done over here. This 2T was upwards, movement was upward. It is plus 2Tx. And the work done by the tension over here, 2T is upward, but the body has gone down by y. So it is minus 2Ty is equal to 0. So what you get is x is equal to y. So you do whichever method, you are going to get the same thing. That's for the movement of pulley. I can apply this also over here, but not required. Velocity of this and velocity of this and this. Velocity of these two parts you can write. Supply of string over here. Okay, that would be interesting. I'll just write. I'll take the velocities as different velocities here and there. We'll see how it cancels out. So, say this body is going up by v1 and these velocities are, say, u dash and u. So this part of the string is going up with u dash. So this part of the string would be coming down with u dash. This part of the string is going up with u. So this part of the string must be coming down with u, no doubt, because these two are fixed pulleys. So if this string is going up with u, this string is coming down with u. Now we have a relation between the movement of the velocity of this part of the string, this part of the string, and this point. So what's the relation? The relation is v1 plus v2 by 2 is equal to the velocity of the pulley. So if this is going up with v, velocity of the pulley is v1, is going up with v, so upward is positive. So u dash we have taken upward, u also we have taken upward. So what you get is u plus u dash by 2 is the equation at this end. Equation at this end would be this whole thing, say the pulley and this mass is going down with v2. So v2 is the movement of the pulley and these 2 points are going down with u and u dash. So again, say downward is positive, then the velocity of the pulley is v2 is equal to downward positive. So this is both are downwards. So u plus u dash by 2 again. So what we conclude from 1 and 2 is v1 is equal to v2 in the directions what we have taken. We have taken v1 as upward direction and v2 as downward direction. So that is what we get the answer from here also, that the velocity will be same. That means the displacement will be same. So what have we done over here? We have not restricted the velocity of this to 0 and this to twice of v1. That is what I said with analysis, that you restrict one side and move it and see the movement on the other side. So had we restricted it to 0, had this u been 0, then u dash would have been twice v. You can see from the formula also. So here we are not restricted and we have given them any velocity they want to go at. So u and u dash, one can be negative also and the other can be positive also. We have given it full liberty of going with whichever velocity possible. It was not necessary in the two analysis cases. One is we restricted it. The other way of analyzing was we moved it and moved both the side by x amount up. Means velocity of v1 was equal to u and u dash. Means v1 was equal to v1 plus v1 by 2 is how we analyzed in one of the cases. In the other case we analyzed by v1 is equal to 0 plus, say, the u dash by 2, where u dash was 2u. So we have analyzed using these, and here we are letting the velocity to assume whatever value they want to be and using the formula which cannot be defied. So again we get V1 plus V1 is equal to V2. So how we have done? We have done by all three methods. I would prefer analyze and just be over with these kind of simple questions without having to write anything. And even if you have to write, this method 2 is the minimum effort method, so you can put that. And for work done, that is also quite fast to write, but then you'll have to put all the T's before you start with the question. So you have to put the T's properly, assume all the pulleys are massless, and that is how you get to the work done method. And obviously this method is just to get your understanding of relative velocity right, so not necessary to be applied in this particular case. So moving on to the next case. So again, two bodies only. We have body 2 hanging from the small pulley and a body 1 which is attached at 3 spots as shown. Now again, you can have the movement whichever way. Which is massive and which is not massive is not the question. If it goes up, this is going to go down, or if this goes down, it is going to go up, and the movement ratio will be the same. So we will move in a direction what we feel convenient. It is, the question may say that the body 1 was going down, so that doesn't matter. To solve the constraints, we'll assume the direction what we want and get the ratio of the movement, and then later on, whatever is the question, whatever is the actual question, we'll represent the answer in that fashion. Okay, so let me tackle this question with our first method, that is by inspection. Now I will always prefer to make the strings loose. So let me redraw this question first so that this diagram is intact. Yeah, so this is the diagram. This is body 1 and that is body 2. Say I move body 1 up. It is everything has been placed flat on the ground. What is going to happen is when I move body 1 up, due to gravity, it is going to go down. But here, I'm not letting gravity play any role, and whatever movement has to be done will be in my control. I'll do all the movements myself. So when I take this body up over, say, here, then what happens? This string falls loose, this string falls loose, this string becomes loose. Everything is flat on the ground. Now I'll move. So if I've moved this body up by x, this loose string what we get over here is x amount, x amount, x amount. Now one by one I'll tighten it up. So to tighten this part up, I'm going to pull this part down by x amount. So I'm just tightening this loose string, I'm just tightening it up and it becomes tight again. So this part has to go down by x. If this part has to go down by x, then I have to move the pulley. I have to move this pulley down by x. So the pulley goes down by x amount. If the pulley goes down by x amount, again I get some loose strings. I'll get loose string over here, I'll get loose string over there. So I've put the pulley down. By the way, I'm not letting gravity do any effect. So I put the pulley down by x, so I get a loose string of x amount over here and x amount over here, because the pulley itself have moved down by x amount. So now let me see how much loose string I had. This part has become tight, so no doubt about there. I've got loose string here, I got loose string here, I got loose string here, I got loose string here, and the pulley is down somewhere over here. So what I do is, I'll just tighten this part up. So to tighten this part up, I'll have to pull this down with 3x. X to tighten this, x more over here. So 2x from there, and then x more over here. So down there, I have to pull 3x to make this part of the string, this string again tight. So this string has again become tight, this string has become tight, but here we have got a big loose string of 3x. Now how to manage that 3x? This pulley has to be pulled down by 3x. So this part, the pulley goes down 3x, so that this loose string, the loose string what happened over here is again tight. But mind you, I've got a loose string of x also over here. So the situation, I'll just redraw the situation over there. This was the initial situation where the pulley was at a certain position in green. You had a loose string x over here and the body hanging down. Now you have made the pulley go down by 3x because you had a big time loose string over here of 3x. So you have made the pulley go down. To tighten this string, to tighten that string, you have made it go down by 3x. So once you have made it go down by 3x, what you see is this part also becomes loose, that part also becomes loose. So you have 3x loose over here, you have 3x loose over here. So how much shall I pull this end down so that everything becomes tight? So how much shall I pull this end down? So to make everything tight, I have to pull x plus 3x plus 3x. So the whole string which has to go down is 3x plus 3x plus x, which is 7x. So that's your answer. If this goes x up, this goes 7x down. Hopefully by other methods we get the same answer. So I'll just repeat this method before we go on to the next one. This method, we first made all the body flat on the table so that gravity is not acting. We moved body 1 x amount up and inspected how much loose string we got. We have not moved any pulleys yet. So we had got 3x loose strings, x here, x here, x here. So we planned to tighten this string up first. So we tightened this string up. So to tighten that string, this had to move down. So this pulley moved down by x amount. So what we got is x loose here, x loose here. That is this and this. X loose here, x loose here. X already loose over there. So to tighten everything up, x plus x plus x, we have to pull this part. We have to pull this part down. So we have to pull that part down by 3x. So when we pull that part down by 3x, what we got is 3x loose and x which was loose from the first movement. From the first movement we had got a x loose over here. So we have x plus 3x which is 7x. So we have to pull this body down by 7x, and that is how we get the answer. Without putting your pen to paper, without marking all these, you can do it in mind. You can just analyze and do it in mind when you have got a hang of it. Before you are sure of getting analysis right, you can go on for more mathematical methods where you can verify your answers or make them your pet methods. So going on to method 2. So shall I show in the diagram itself? I'll show in this diagram. When this body goes up by x amount, this body goes down by y amount. So I already know that y is multiple times x. So I'm just making that arrow as a big arrow, but you might not be knowing that before you do it. So hence you should have an analytical mind over here so that you analyze which movement is more. If you get the movement of this body as 1/7 the movement of that body, means your brains in physics is not working the way it should. Now, if this body goes up by x, we'll count all the string lengths individually. Length of each section of the string and equate it to 0. So we have got 3 strings over here. We have got this number 1 string, number 2 string, and number 3 string. So first, using number 1 string, this goes by x up. So this pulley has to go down by x. So that's it, minus x, and this pulley goes down by y. So you can write plus y. So minus x plus y is 0. Now, if this goes down by x, what has happened to this section of the string? What has happened to this section? I think I'll have to redraw this part so that you understand it well. Okay, so now a bit safer method for many of you. So that is counting the reduction and increase in length of the string. So we have got 3 strings over here, one in green, one in orange, and one in purple. So when this body 1 moves up by x, we are guessing this is moving down by y amount. So what is happening to this green string? So I'll write a separate equation for green, separate for orange, and separate for purple. That is how I'll be super safe in doing the question. So what has happened to this section? It has reduced by x, the green string, and this section, assume that this pulley goes down by some amount, say p. We don't know yet how much. Okay, so it goes down by p, and eventually this pulley is going to go down. So they say this goes down by q amount. So what has happened is the green string would have increased, the pulley has gone down by p, so the green string would have increased from here to wherever it goes by amount of p. So we get minus x plus p is equal to 0. So we know what it means. It just means that how much ever the body has come up this side, this pulley is going to fall down the same amount. So it goes down, goes up x, so it goes down x. So p is equal to x. Now here, so I'll instead of p, I'll be writing x. I'll write p and then later replace it by x for the next string. So in this orange string, what has happened? It has gone up this point. the orange one. So this point has gone up by x. This point, this pulley has come down by p. So this point has come down by p. So this section has been reduced by x plus p. So it has been reduced by x plus p. So minus x minus p. That is how it has been reduced. What has happened to this section of the string? Now this part has gone down by p. So this has gone down. So this section has reduced by p because the pulley has gone down. So this point has gone down by p. And this point, the other end where it ends, that point has gone down by q, which is increasing the length. So it has increased the length by q amount. So what we get over here, remember your p was equal to your x. So what we get over here is q is equal to x minus x on the other side. So minus x, so that is your 3x. So that is what we had done through the analysis also. This is going to fall down by 3x. Now the last string, the purple one. Now this pulley has gone down by q. This point in the purple string, we are going to analyze the length of the two sections. So this has gone up by x, but the pulley had come down by q. So the remaining length is x plus q shorter. So it is minus x minus q. X up and q down. So it has reduced the length of the section by x plus q. The other section has also reduced because the top point has come down by q amount. So it has reduced by q, but the bottom point has gone down by y amount. We are assuming it has gone down by y amount, which is a correct assumption. So it has increased the length by y. So what do we get from there? Remember, your q's are equal to 3x. So 3x and a 3x and a x makes it 7x. So we get y is equal to 7x. So thankfully that answer is same as what we had got earlier. So we have this y is equal to 7x. So that's your method 2. So we have got method 1, we have done method 1, we have done method 2. Just give it a go and do the method 3 yourself. And then if you are wanting to write the relative velocity equations and all, you can write that equation also and verify what is happening over here. Not required. Obviously all methods are not required. Why am I telling you in all methods is whatever suits you best, do that method. So I'll just quickly do the work done method also over here. So all strings will have different tensions. We will assume ideal pulley. So say this string is having a tension of T. T up, T down, T up, T down. Every time I'll make both the T's pulling both the ends. So this becomes 2T up, 2T down, 2T down, 2T up. So this is 2T, 2T. This pulley is massless. We are assuming it is massless. So the tension in this green string becomes 4T up, 4T down, 4T down and 4T up. So let's see what is the work done by the tensions. So one is the input end, one is the output end, whichever end you consider. The work by the tensions. The tensions, the total work done by the tension over here is the total tension force over here is 4T plus 2T plus 1T. How much is that? So I'll write in blue. That is your 4T plus 2T plus T. That much, all of them is this totally is a total force on this, and all of them have moved by x amount. So the work done by this force totally is x, so much into x. So that's the work done at this end by the tensions. What's the work done over here? Mind you, just note that the direction of the tension and the direction of movement is same. Hence we have written plus over here. And on the other side, the tension is up, but the body has gone down by y. Hence the force is minus T. T was the tension over here, and y is the movement. They are opposite in direction, so minus T y. So total work done by tension will be equal to 0. What we get over here is 7T x minus Ty is equal to 0. Again we get your y is equal to 7x. So again quite a safe method over here. So if you ask me, I would prefer method 3 over method 2 in this particular case to be safe with the answers. So this becomes my preferred method. But generally I will analyze first and get my answer. I'll get a feel of what's the answer. If you're not very sure, you can go for a hunch and then do these methods. Okay. And the day your hunches are going to be right, spot on, you can understand that you are good in this section of physics, in the mechanics. Now the last one, so I'll call these velocities P as velocity and Q as velocity in this case, and I'll just do it again. So we have to write the equations for the pulleys. So equation of the pulleys. So say we are pretty we are not going to write equation for this pulley because we know that how much ever is the movement up, that's the movement down over here. So what's the velocity of the pulley over here? So here this is going down, this has come up with x, so this point is going down with x. So this pulley has got a movement of x. So applying that formula, it is x down. Say down we take positive. Now what about this end? What is happening to this end and what is happening to that end? So this section has come up with x. So this section, since the wire is always tight, this section has come up with x, and since the string is always tight, this will be going up with x. So one side is going up with x. So V1 will write it as minus x because it is going up with x. So what happens to the next section? What is happening to the next section? Say it is going down. Say it is going down with a new variable, say a. So this part is going down with a. So what we'll take is plus a, plus because down we are taking positive, divided by 2. So what we get over here is 2 into x plus x, which is a is equal to 3x. Thankfully, we knew that it is going, if it is coming up with x, it is going to go down with 3x. So this part now, we know that this part now, this pulley now is going down with 3x velocity. All these are velocities now. I'm just not renaming them. So x is the velocity, y is the velocity. I'm not renaming them. So this has gone down by 3x. So again apply the pulley formula. 3x is your pulley velocity is equal to velocities of the string on the either sides. So this has come up with x. If this point has come up with x, then this point must be moving up with x because it's a tight string. It is all the things are going together. So this was going up with x. So this point must be going up with x. Same logic as I used over here. This point is going up with x. This point is going up with x. So x up will take as negative because 3x down was positive. Plus, I don't know the velocity of this part, so I'll call this part velocity as say b. So what do I get over here is plus b divided by, so down is b, down we have taken positive, by 2. So what do we get over here is b is equal to 2 into 3x, which is 6x, plus x, which is 7x. So b is 7x and b is directly linked to this. So your y is equal to b. Your y is equal to b. If this point is going down with b, then the body is going down with b. So we get b is equal to 7x. So this is more for fun. You can check out it is all coming right or not. So we have done by this method also, but not required obviously. So I would suggest you do by any two methods, and if you get the same answer, then you would be damn unlucky if that's not the answer. So let us take more questions where we have more than two bodies. We have three bodies. That might be a little interesting. So there I am not going to explain you by all the methods. You do it for yourself, and I'll pick any two methods of my choosing and do it. So this is your first case of three bodies. So let us call this as body 1, this is body 2, this is body 3. Now what you can note over here is, unless until I know the movement of two bodies, I don't know how much will the third body will move. Say this body number 2 was, or body number 3, that's the easiest to imagine, that body number 3 was stationary and I move this body number 1. So if this body number 3 is stationary and moving this body number 1, body number 2 is going to go with a certain velocity, with depending on what's the velocity of body number 1. Now suppose I let the body number 3 go up or go down. So I am moving body number 3. In fact, let me make this stationary and make body number 3 go down. So this is going to go up by a certain velocity, and we have done a lot earlier. So we know if we move 2x down, it's going to go x up only, and vice versa. If I move it 2x up, it is going to go x down. But if both are moving, then there will be some other movement. That means I need to know the velocities or movement of two bodies to get the movement of the third body. And it is, if you feel that this goes up, then this should go down. No, not necessary at all. So let me do this. Like this goes up with 3 meters per second, and this also goes up with 4 meters per second. Why and all? Maybe there was some force on this body and this body was being pulled the other side. So both were going up. We are going to do constraints. If these were the movements due to whatever reason, then what is the movement of this provided all the string is tight? It is different from a situation where I say that all has been let go. They have some masses, and then how they move. Then maybe this was moving down, that was moving up, or maybe this was also moving down and this was going that way. So that's a different doing laws of motion and solving your forces. By the way, can there be any situation such that nothing moves, everything is frictionless? This is a very, very massive body, say 1000 kgs, and everything is frictionless. Will there be a situation where nothing moves? No, there won't be. Due to the weight of this body or this body, this string has to have a tension. If this string is having a tension, it is going to pull this body, how much ever low force it is. Even if it is 1 gram force tension in this, it is going to pull the body and will create an acceleration accordingly by the formula F is equal to ma, provided there is no friction. So practically it is possible, because practically no friction is very difficult to achieve. Okay, getting back to the situation, and say I've written the numbers 3 and 4 and I want to know the velocity of the body. So what will be the velocity of the body? So according to this, intuition says the body will be moving that way. Now let me do it, my old method or my first method of analysis. So I am inclined to move the movable pulley first, and everything is at their own place. So if I move the movable pulley up by 3 amount, so 3 is given. So if I move it up by 3 amount in a second, so we'll have 3 loose here and 3 loose there, 3 and 3 loose. So what we have got is 6 loose. We have not moved this yet. So to tighten this, I'll pull this by 6, so that the 3 here and the 3 here gets tightened. So I'm pulling this by 6, so I've got amount of 6, but this has not moved. That's the situation when this was going up by 3 and this was stationary. Now this has become stationary. The one which I have moved up by 3, now it is stationary over there. It is stationary over there. I have tightened these loose strings by pulling 6 on the other side. So now this, I'm moving the body number 3 now with 4 movement up, 4 meters in a second up. So I have moved it 4 up. So what happens? This is stationary. So the whole string is stationary. So this is stationary, stationary, stationary pulley. So if I move this up by 4, this part will go down by 4. If this part goes down by 4, this string is going to go up by 4, and hence this string has to be pulled by 4 more. So what do I get is 6 plus 4, which is equal to 10. So I guess the answer is 10 meter per second is with which this body will be going that side. Who is making it go is another story. There might be some force over there which is making it go that side. If you let go, it is just going to go down. So that's your method 1, and we get your velocity of this end is 10 meters per second. I would have rather taken just variables and explained how the variables are related, but let's do this by the next method also. So what is that? You have to write the increase and decrease in the string length. So going from this side to this side. So how much this reduces by? This section reduces by 4. So I'll write what? I'll write minus 4 is how much this reduces. How much is this going to reduce by? This pulley is known that it has come up by 3. I don't care what has happened to the string and where it should go, because there is some other force which is governing everything. This pulley has come up by 3. So this section of the string has reduced by 3. So I'll have a minus 3 again over here. And what about this section of the string? That section has also reduced by 3, because the pulley has ultimately come up by 3. So this pulley has come up by 3. This section length has again reduced by 3. So minus 3 over there. And this section has increased by a certain amount, unknown amount, by a V amount. So it has gone by V. So this section has increased by V. So I put plus V over there. And total increase or reduction should be equal to 0. So that is what I put. And we get V is equal to 10 again. So that's your method 2. Quite safe. And then, okay, by work done. So let us just put the tensions. This is T, 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 T. So this must be 2T in an ideal case. This is the same string, old string. So T, T, T. So we have to write the work done at wherever is the input and output points. So suppose you are pulling this and the output is these two or whatever. These are the points where you have the inputs and outputs. So the work done by this tension, it is moving this side by V amount, but the force is that way. So say V is the displacement, 3 is the displacement, 4 is the displacement in a second. So the tension is towards the right and the movement is towards the left. So this work by this tension is negative. So what we write over here is minus TV. This end, You have 2t which is upwards and the body movement is also upwards. So what we write is plus, because they are in the same direction, 2t is the force and the movement is 3. So 2t into 3, that's the work done. For this end, again, the body is going upward, tension was also upward, so it is plus for that. So getting your minus and plus right is the key. You have to get your minuses and plus correct. So what do we get over here is tension T into 4 is the moment. I'm sorry, this is 4, so 4 is the moment. So total work done by the tension must be equal to 0. So what do we have? All T's cancels. You have minus V over here. You have plus 6 over here. You have plus 4 over there is equal to 0. Gives you V is equal to 10. So the unit that was, we did work done as, these were as meters in a second. So you could have said these to be powers. So unit over here is meter per second. So that's your third method in this. And you may apply the fourth method also just to check how is the movement happening over here. So let's go on to the next question now. So what we get over here is 3, 4 and 10. Say we have called the values as x up. Since I have written up earlier, I'll just continue with that, and y up. Then what would have been the movement? The movement would have been due to x up, this will create a 2x loose string, and due to this y will be supplied. So we'll have 2x plus y as the movement over here. So x was 3, so 2 into 3 is 6 plus y 4. So you can get this very fast by just inspecting. So we'll go on to the next question now. So again, more than 2 bodies, say body 1, body 2 and body 3. So if you know the movement of 2 bodies, you can tell what is the movement of the third body. If you just know the movement of one body, you can't say how much which is moving unless until you know the masses. So, and why do I say unless until you know the masses? Because if they are a certain mass, say 2 kgs and 3 kgs, and this is whatever kgs I'm moving it with 2 meter per second. So I'll do this experiment 100 times, still the movement of both of them will be same, because it has got a certain pull from gravity and a certain release I am giving it from there. So I don't think that if I do the experiment and again very carefully, if I repeat the experiment again and again very carefully, the movements are going to be different. So when masses are given, that becomes a laws of motion question, and we have to figure out using all the forces and all that how much which will be moving. But unless until that is given, by the way, speaking of that, if all three are also just let go and movement of nothing is given, still you can figure out how much which is moving, and all the time it will be the same answer if the masses are known. If the masses are not known, then we need to give the movement of any 2 body in this case to get the movement of the third body. So take some time doing it, and at least do it by 2 methods, and lot of movable pulleys. You can verify this equation to get a hang of that equation also. So that's hardly required, by the way, but still. So let me analyze this for you. So my favorite spot to start is a movable pulley. If I move this by x up, what do I get? I get 2x loose string. So I'll tighten that. Nothing has moved yet. No, nothing else has moved yet. So this has gone up by x. I've got 2x loose string. So that 2x loose string, x over this side and x over that side, I'll tighten by pulling this x. So I've got 2x loose strings. So I'll pull this by 2x, and the string on this is tight. I've not moved this yet. I'm just planning how much to move. So suppose I move this also by y up. Having a loose string over here doesn't make it necessary that you have to move this body down. This can be moving anywhere. So I'll take it up so that you are not confused. Mind you, I've got a loose string of 2x till now without the movement of this body. Now I've moved it up by y amount. So what do I have is y plus y, 2y extra loose string. So how much I've got? 2x over here and y plus y, 2y over here. So this part I have to rather pull by 2x plus 2y to make everything tight again. So when I pull that up by 2x plus 2y, this part has to go down by 2x plus 2y. So what I get is the movement of this has to be 2x plus 2y. So if this moves x up, this moves y up, this goes 2x plus 2y down. I hope you can do in the case when this would have gone down by y, then what would you have written? You would have written a 2x minus 2y. So you can practice with some numbers over there. Let me put another method to this. So what would you prefer? Increase and decrease of length. Okay. Okay, I'll write all the methods. So this reduces by x minus x. This section, again, this has gone up by x amount. So this section again reduces by x. So minus x over here. This pulley has gone up by y. I don't care what has been supplied and all. I've just moved the pulley and then writing this length of the section. So your mind should not work that I've given string and hence it should fall down and all. We have to see where it has gone, and no loose strings, all tight strings. In this method too, everything is tight. So if this pulley has gone up, this section has reduced by y amount. So minus y. This section of the string has also reduced by y amount. How much is y and x? How y and x is connected is not yet known. So minus y. So the pulley has gone up. So this section has become whatever it was earlier minus y. This is also whatever earlier minus y. And this section, it has gone down, say by z amount. So this section has increased by z. So plus z is equal to 0. So what you get is z is equal to 2x plus 2y. So that's your method 2. Method 3 will be a similar thing. So this is being pulled up by T tension. The T tension goes all over. It's a single string. So this must be 2T and this must be 2T. So it goes up by x. So the work done over here is 2tx. This goes up by y. So it is 2ty. Direction and displacement is same. This is t up but goes down by z. So minus tz is equal to 0. So again we get z is equal to 2x plus 2y. And then comes a pulley equation, which is the least preferred in this case, not at all required. This movement is 0 because it is attached to the wall. This movement is what you want to figure out. I know it is 2x, but you want to figure out that, and this pulley movement is x. So what I write, how do I write the formula? X is the pulley movement is equal to one side movement, which is 0. Other side movement you want to find out. So call it as, say, a divided by 2. So what you get? A is equal to 2x. So you know that this movement is 2x. So this 2x goes on. So this side of the pulley, this string is going down by 2x. This pulley is going up by y. And this is, say, b you want to find out. So what do you write? Up is, say, positive. So y is equal to, down is negative. So minus 2x is the movement this side. And that side, say, b is up. So plus b divided by 2. So what do we get over here? We get is, what we get is b is equal to 2y plus 2x. So that's your b. How much ever b is supplied, this is 0. You can write the formula again, or simply this ends the question. This, if this is going up by b, this has to go down by b, and b is your 2x plus 2y. So that's your last method over there. So if I may mention this also as a method of solving, that's for you to understand how velocities work, not particularly solving the question. As you can see, these two are giving the answers much faster. Now another question for you. So have a look at these two questions and do both of them. I'll discuss both of them together later on. One is with variables. You have to find how much this moves. And if your intuition is in the right direction, say it moves by z, then put the direction also right. So unnecessarily getting a negative and then making it positive is like revealing you did not know what is happening. So you should be in full control of the situation. So guess in a very logical way where it is going up or down, and then accordingly you do it. And if it is like it can go any which way, depending on how much is the x and y, then you can write any direction. Similarly over here, and then later on, when you have guessed that it can be any which way, if say x was way greater than y or y was way greater than x, depending on those values, then you'll put the values in your final answer and see whether your reasoning of going in the right way was correct or not. Here I've put some numbers straight away for you, so that no variables are required. You can straight away do with the numbers. So have a go at it. Let's start with this one. So I generally prefer loose strings. I've got a movable pulley. I would have preferred this going up and then studying the other movements. But it's okay, since the value is given, we are going to do the way it is given. So if this pulley comes down by 4, what is going to happen? You have to have a supply of 4 and 4 string over here and there. So 4 over here, 4 over here. So where is it going to be supplied? Maybe 4 from this side, maybe 4 from that side, but it is not given it is 4. Had it been 4 up, this would also have been 4 up. Both would have gone 4 up and this would have gone 4 down. So it is similar to one other situation where you had a big pulley over here. Instead of these two ending in masses, there was a big pulley over here in this very video a little earlier. So okay, coming back to the analysis. So if I have pulled this 4 down, then I've got 4 extra string on both sides. So let us see whether anybody is supplying the string or not. So this guy is not supplying the string. This guy is in fact pulling it down. It is pulling this mass down and it is reducing the string. So who is going to supply all those string? So if this pulls down, this end is pulled down by 2, you need to have 2 going up. You have to have 2 extra string coming from somewhere. So this guy is going to do that. I've made this pulley stationary. And first I just move this body down. So this pulley is stationary. I move the body down by 2 meters and this pulley is stationary. So this has to go up by 2 meters, or stationary pulley, it has to go up by 2 meters. Now I am done with the movement of this. It has come down to its new position and it is not going to move. So with respect to the ground, it was 2 meters per second. So after 1 second it is here. So I have made that 1 second, that movement first for this. So it has come down by 2. I have made this steady over there. That is possible in a situation without any strings breaking. So I have this stationary over here. So this guy supplied. So this moved up by 2 because of this coming down by 2. Now this is stationary and we have this pulley which is now moved down by 4 meters. So if I move down by 4 meters, I have to get 4 plus 4, 8 extra string. Who is going to supply that? Now this one will not supply. Why? Because it is stationary now. So when this pulley has come down by 4, that extra 4 and 4 has to again come from here. It has to go up and it has to give. It is not like going down. So both time it went up, 2 up and 8 up. So what do I get? I get 10. So that is by analysis. By increase and decrease, this will be plus 2 this side. This has gone down by 4. So plus 4 for this section, and for this section it is again plus 4. It's the same string. It is one single string. So one single string I write in one go. And this has gone up by a certain amount, say x. So that is reduced by x is equal to 0. So what do I get? X is equal to 10. And similarly with tensions. So you'll have a 2t over here. So 2t into minus 4, here t into minus 2, and here you'll have a t into x. So 2t into minus 4, which is minus 8t, and minus 2t, so minus 10t plus tx, you'll get x is equal to 10 again. And the last method, okay. Now coming on to this. Method 4, you can apply if you want. This may be one of the preferred methods for this. I mean, it is equally short as the other ones are. We analyze these 3 parts. So we know the velocity of 2 parts already. So in this situation, fortunately in one go, once we apply that, we are going to get the answer. So this 2 was coming down. So this part is going up with 2. This part of the pulley is going down with 4. So this 2 up, this string is 2 up, this part is 4 down. And this over here is going, say this was going up with x, so this is going down with x. X is what we have to find. So we write the equation of the pulley. So pulley movement is 4, say down is positive, so down is positive is equal to 2 is up, which is negative. X is positive, so down is positive, so plus x. Had we taken x as up, then we would have taken as minus x, but we already know which way it is moving, so we have taken plus x now, and then 2 into 4 is 8, 8 plus 2 is 10, so you'll get x is equal to 10. So this x down will be that x up, so that will be the movement. So all methods done over here. Now going on to this question, x and y. So again, by analysis, if this is a movable pulley, I'll just go on attack on the movable pulley first. If this movable pulley goes down by a certain amount, by say a, then this would have fallen down by 2a, because you would have got loose string here and here. So if this is going up by a, this is going up by x, this would have gone up by x by 2. So x by 2 up gives a x by 2 string here and x by 2 string here to be pulled in from one end. This is tied to the wall, or this is tied to the ground, so it can't move. So this has to go up by x. So if this is x, this is x by 2. So if this part is going by x by 2 up, this part is coming down with x by 2. So if this part comes down with x by 2, now if these were equal masses and whatever, the both might not have been moving with respect to each other, so both would have gone down by x by 2, but we already know the movement of one. So if we know the movement of one, we can tell the movement of the other. So if this goes by x by 2 down, what do I have is, I have a loose string of x by 2 and x by 2 on both sides. So this, I'll just move one body down first and then fix the pulley. So this has to go down with x by 2 plus x by 2. That is equal to x. It has to go down with x. I'm just fixing this. I have not moved this wherever it was. I've just fixed it and I've just moved the pulley down. So pulley has come down with x by 2. So this string just rolls over and this drops by 2x. But then this body is not fixed, it is also going up. So now I move this body. So I'll do everything one by one. It is not like simultaneously I'll do things. So once the pulley, I have put it down over here, I fix the pulley. Now I move this up. So if I move this up by y and this is fixed, then this has to go down by y. So this totally goes down with x plus y. How much ever this was, plus a y. So what we get is, if this is x and this is y, if this is x and y, this goes down with x plus y. Let us verify it by the other method, which is increase and decrease in string length. So what we have is, we have three different strings in fact. So that's your green string, that's your, say, blue string, and then the purple string. So there are three strings, so I would rather prefer method 3. In method 3, you don't have to write 3 equations for 3 different strings, but since I made the colors, I'll just write them off. So what happens in this method, this section, this is going up. So this green section, and the pulley goes up by a certain amount. So let me write some variables. So pulley goes up by, this is not known, so pulley goes up by a, this goes down by a, so this pulley is going down by a amount. So first the green string. In the green string, this pulley has gone up by a, so this section has increased by a, so plus a for the green string. Similarly over here, since the pulley has gone up, this section length has increased by a, but it has decreased by x. So this part has gone up by x, so minus x is equal to 0. So total increase decrease is equal to 0. So what we get is a is equal to x by 2. So we already knew that this is x by 2 by inspection. So x by 2. What we have in this blue string is, this blue string has reduced by a amount minus a over here, and this blue string has increased by a amount on that side. So plus a is equal to 0, which is a known thing. So that means how much ever it has gone up, this has gone down. Now coming to this purple string, this section, now you have to carefully see, this section has reduced by y from this end and has reduced by a amount from that end, because the pulley has come down by a. So this section has become reduced by minus y minus a down from there and y up from there. Now if this goes a z amount down, then let me write the equation of this section. This section has reduced by a from top, but from bottom it has increased by z. So what we get over here is, your a was x by 2, so twice of a, so z is equal to x plus y is what you get again. And through tensions, you have, this is T over there, this becomes 2T tension in this, 2T tension in this. So this is again T and this is again T. So T tension, T tension, T tension. So work dones are T in direction of x, Tx, T in direction of y, Ty, T opposite to z, minus Tz equal to 0, again gives you the same relation. I hope with all these methods you're not going to make an error in solving. If you are not getting the same answer by all methods, then you are definitely wrong with one or wrong with both. So get your concepts right, rewatch the videos for these kind of questions. So let us move on to the next kind of questions. So where one body is on top of the other body, and initially I'll do one without any angles involved. Now look at this question and give the answer within seconds just by analysis. This is going by 2 this side, this is going by 3 that side, and where it should go with how much of velocity, which side, up or down, and how much of velocity. So I'll just urge you to do it by analysis. It is a very simple one. So what is your analysis? How do you do in analysis? Everything stable and move one thing. Say everything, this pulley stable, this is the movable pulley, and this thing stable, and this just goes by 2 forward. Then what happens? How the string will go down, how much it will go down. And once that has happened, it has finished its movement of 2, then this stays put. This stays where it is, and you move the movable pulley, which is going to make this 3 go 3 up, so 3 up, so 3 in. So 3 in, so how much of string will go over there? So I hope you got it. From here, if you loosen 2 with everything stable, so this has to go down by 2. If you move this by 3, then you'll have a loose string of 3 and 3, which is 6. So you have to go down further by 6. So 6 plus 2, your answer should be equal to 8 down. So I hope you have done in almost no time. So one of the ways was, if everything is fixed, this goes by 2 forward, then this will give the string 2 down here. So this will go down by 2 if this goes forward by 2 and everything is fixed. And then when we move this pulley by 3 this way, so that this goes up by 3, then we'll have a loose string of 3 and 3. So to tighten that, this has already completed its movement of 2. I can't do anything to this side, so this string remains put where it is, and this stays put where it is. So I have to give 3 plus 3, which is 6 down over there. So I should get my answer as 8 meter per second down. So 2 supply from here, and 3, which is 6 supply from there. Have a look at this question now. It's pretty much the same concept. It is the same concept, in fact, but there is one unique point over here which might be a point of consideration while we are doing the question. So that will come when we are taking tension, when we are doing through the tension method. But let us just get the answer by analysis. If I move this by x amount forward, what will happen? I'll get a loose string of x over here, I'll get a loose string of x over here, loose string of x over here, because all of this would have become loose by x, nothing to this remains straight. So this is a pulley on the mass. So this pulley is also a movable pulley. So this has gone forward. So I'll get a loose string of x over there also. So ultimately x, and x. We have got 4x loose string. So this has to go down by 4x. So that is quite straightforward. But somebody who wanted to do it by the third method, that is total work done method, then let me write it properly. Tension. All sections I am drawing the 2 tensions pulling the bodies. Now where we used to ignore a lot of places where things were not moving, so we used to ignore those places for tension. But here, look very carefully, that points where we have to write the work done by tension is this point, it is this point which is being pulled by 2t, and it is this point which is pulled up. Now this point is what I was referring, where you might miss. So this is attached to the block and the block is going forward. So this tension is responsible for pulling the block. So this tension is doing work and making the block go forward. So writing the equations, the orange ones are the tension. So let me write. So this goes in the direction of tension, in the direction of tension, in the direction of tension. How much x, and x? So we have 4 times t into x. Tx, or 2t into x rather over here, but it's the same thing. So this is what you might miss out. So this is important over there. And here it goes down by, say, a y amount. So a y amount, it goes down, tension was upward. So minus ty is equal to 0, y is equal to 4x. So while you are doing with tension, be careful. When doing with increase and decrease of length, that will be quite straightforward. In this case, this would have reduced by minus x, remains same, minus x. So minus x, minus x, minus x, minus x for this, and this would have increased by y. So we would have got y is equal to 4x. Quite unlikely that I would be wrong by all four methods. Okay. So the point over here, but the only different point over here was there was a pulley which was attached to the block. So when the block moves, the pulley moves. So this becomes a movable pulley. Plus, for sake of forces and all, whatever force is acting on the pulley is acting on the block. So if I am pulling my hair is attached to my body. So if I pull my hair, my body gets pulled. So same way, if the pulley is getting pulled, the block is getting pulled. So this force, this T is acting on the block. If somebody has to write an equation of motion in the front direction, then the total forces on this block in the front direction was T, 4T. 4T was the total force in the front direction. So the acceleration in the front direction will be given according to F is equal to ma, that is 4T is equal to mass of this block 2 and acceleration of this block in the horizontal direction, which is the only direction in this case. So let us now move on to cases where things are inclined. Now let us analyze these questions where some angle is involved. The movement of the body and the movement of the string is not in the same direction. In this case, in that case, in here, the movement of the body and the string is in the same direction. So had I given it like this or this, it would have been the same case. So, and this one is a rod, is a rigid rod. So this is not a string. But anyways, all these are always tens. It is all extended. So here also the length is maintained. Here also the length is maintained. So all can be dealt in a similar fashion. So let me first discuss this question and see exactly what is happening over here. Once we have understood what is exactly happening over here, we'll devise some simple methods of doing it. I'll list those methods over there and you can apply those methods over here. So first thing what I'd like to ask you is, I'll redraw this question. If this body 1 goes down by a certain amount x, will this other body, which is body 2, go here by say amount y, which is equal to x? Will this x be equal to y? That's my first question. Just think, this is your fixed pulley. This is constrained to go horizontally. The tension is such that it is not lifting the body up and it is going horizontally in that direction. So when it goes down by x, will it go this side by y or not? This side. Will it go this side by y or not? That is my question. I hope you have got it right. What I think, it is not going to go by y, it is not going to go by x. If this is x, this y is not going to be equal to x. Y is not equal to x. So next I would ask you, why that? We'll just see. What do you think? Is y going to be more than x or less than x? The movement over here, say a 2 centimeter movement over here, generates a 2 centimeter movement greater than 2 or less than 2. How much it generates? So think for a while. So what I guess is, if this body moves from this point to this point, this string, now it will be like this. Now the reduction in the string length, whatever was the length earlier, say the length was L1 earlier, now it is L2 this side. The reduction in the length is not equal to y. Your y is greater than that. If I make a, taking this as a center, if I make an arc, this is your L2. That's your, totally was your L1. So this much part is your L2 because I have taken an arc and cut it off. So this much is how much, this green part is how much the string has been reduced by. This green part is not equal to this purple length which was your y. Your y is much greater than that green part. So if you move this much, if you move this purple length, then the string length which is going to go to the other side, the string length which has gone to the other side, which has reduced, is only the green part. So we see that this purple is not equal to green. So the movement, this much movement, this y purple movement is going to cause this green movement in the string. It is going to let go of this much of string from this side of the pulley. So that's the green one, what we have to find. and this is how much it is going to fall. It is going to fall by the same amount as much it goes. So say this was x, so this is your x. So x is clearly not equal to y. So this is what is happening. I can go further in this diagram to get a relation between x and y. In fact, I'll do that. So if you can look at this part properly, or if we can zoom into this part for a while, and then we'll zoom out. So what we have over here is this angle. We know this angle. This angle is theta. So anyways, before I had to get the answer, I wanted you to understand whether this answer is going to depend on theta or not. When it goes down and theta is say 30 degree, that time our two movement over here is going to create some movement over there. So we have analyzed and we have known that a two movement over here is going to create more than two movement over there. Now is that movement dependent on theta or not? And if it is dependent on theta, then if theta is very slant, then the movement is high, or if the theta is quite high, almost 90 degree, then the movement is high. So I'll just repeat my question. I'll make the diagram and reframe the question. Had the case been like this, and you move down by say x amount, which has to be compensated by horizontal movement in this. That time a big horizontal movement is going to compensate for x, or a small horizontal, and the other case is the string was very slant and you move down by x. Then let me just answer it for you. You may pause for a while and think. Yeah, so the point over here is, if it is very slant, it is absolutely slant, then the movement x over here is equal to the movement x over there. Now in this case, it has to go x this way, it has to go some amount this way, that is y this way, such that x movement is created. So y this way is almost going to release, it is almost going to release y amount of string that way. If you go y this way, it is going to release y amount almost, not totally. Here if you went y that way, it was fully releasing y string that way, and this went down by y. If you went y that way, the string release was y. But if you go y horizontally, the string which will get released will be not y but less than y, almost y but less than y. And if you are like this and you go y this way, and you are here, then the string release is hardly anything. This amount of string release is almost zero. So movement, when you are vertical, then the movement is hardly causing a movement on the other side. That means to have a x movement, this has to be a big time movement. A big time movement when the angle is high. So what we are seeing is, what we are analyzing is, at big angle theta, when the angle theta is big, that time your y is much greater than x. And when angle theta is almost 0, it is small, then y is almost equal to x. Let us see after getting our answer whether this part satisfies or not. So this is how we are analyzing, and after getting a mathematical expression between x and y, this thing should come all right. If it is involving cos and sine or whatever, this should satisfy, because this is what we have thought, and our thinking is the main driving force behind all our questions. It is not the maths but the thinking. In physics you have to have your analysis right, your thinking right. Okay, so let's zoom on to this part and check out what's the expression. So I'll just redraw this part, or if you can see over here, I've drawn an arc and I'm not going to disturb this angle much. So if I'm not going to disturb this angle much, I'm just going to go a bit ahead. I'm going to go dy and I'm going to study dx. The ratio is going to remain the same for that angle theta. So the angles are very small. This angle, this is an arc, so this angle is almost 90 degree, because this becomes the radius. That's also the radius, by the way. So the radius is 90 degree to the arc. So this becomes a triangle over here. This orange, purple, blue, that becomes a right angle triangle over there, of which the purple part is the hypotenuse. So if the purple part is the hypotenuse, what's the relation between them? The relation is your x is equal to y cos theta. So that is what you are getting your relation as. That means if you move y, then the string, this blue length string becomes lesser, this orange length string it becomes, and the difference in the blue length and the orange length is equal to this green length, which is x, which is related in the triangle like this, and it is dependent on the angle theta. So I did not make a big triangle, I'm just going, I should have written dx over here and dy over there to get the exact relation. And if I go beyond a certain distance, then the angle is going to change. Then your relation between dx and dy is going to change. So what we get over here is, if I go dy, it goes dx. Dx is equal to dy cos theta. So if the string is released dx, it is going to go dx down, and this is going to go dx down. So in dt time the whole thing is happening, then I can just divide by dt both sides and can say the velocity this side, say velocity of body 1 v1 is equal to v2, velocity of this along y is v2. So y was along the horizontal, so v2 cos theta. That is my relation using this diagram method, which I am not persisting with. I am not going to do this later, so you can just note it down. So this is one of the fail-safe methods if you are good in diagrams and all. And plus this kind of diagram is going to be used later on also in dipole, in your wave optics. We are going to use this kind of diagram. So if you draw once or twice this thing, you are going to get the exact thing what is happening. Now is it satisfying this? At big angles, your y, which is the movement of the block 2, will be much greater than x, meaning to say v2 will be much greater than v1. So when the angle is big, it is almost 90 degree. When it is almost 90 degree, then cos is almost 0. If cos is almost 0, then your v2 into almost 0, so v2 has to be a very large value into a very small value of cos, is going to give you v1. So v2 is going to be v1 divided by cos. Cos is going to be almost 0, so v2 is going to be a large value, which is coming correctly as we had thought. And when angle is almost 0, when theta is almost 0, so cos 0 is 1, that time v1 comes v2. That is this case when the angle was 0. So this is a low angle almost 0, and this is a 0 angle. So at 0 angle, obviously your v2 will be equal to v1. That's v2, that's v1. So this bite diagram you can say is one of the methods, not preferred, but I'll just list it down when I'm writing the methods. So another easy method would be, so I'll just write the answer over here by the way, v2 is equal to v1 cos theta. That's your answer. I'll clear the board. So the most preferred method in such cases, I would say, would be this. So pay attention to this. This body was going forward with v1, but we'll try to find out the component of the velocity along the string. What is the component of the velocity along the string? And then 90 degrees to the string. The velocity which is 90 degrees to the string, this is your string, and this point moves 90 degrees, doesn't create, for that instance, for a very small movement, say dw movement or whatever, very small movement, for a very small movement, it doesn't create any slackness or tightness in the string. It doesn't release any string or doesn't take up any string. So after a small movement in 90 degree direction, the string is still on the pulley in the same way, and nothing moves over here. So 90 degree component, if the body is moving 90 degree, same as something is hanging over here and here, and this body is dangling this way, 90 degree to the string. If the body is dangling this way, this is not going to move. It is neither pulling the string nor letting the string go off. So we are going to divide this velocity, the body was moving that way, into two components. So yes, we are going to use our vectors and utilize all that math what we have learned earlier. So vectors is what we are going to utilize now. In the next method, I'm going to utilize calculus. So when you are wondering that why we are doing all those things, everything will get utilized in some question or the other. So those were basic tools like addition and subtraction in earlier classes. So using vectors, we'll divide into two components. So what are the two components? So component this way, this angle is your theta. So this angle is your theta. So this is your V1 cos theta and this is V1 sin theta. So due to V1 sin theta, no string is getting released. And what about this? If the string is going this way with a V dash component along the string, if the point is going along the string with the V dash component, what is going to happen? This is going to go down with V dash. So along the string it is V1 cos theta. So this is going to go down with, sorry, this was V2. I'm so sorry. This is V2, V2, V2. So it is going along the string with V2 cos theta. So this is going to go down with V2 cos theta. So what do we get? We get V1 is equal to V2 cos theta. So that is how we got it earlier also. That's the same thing what we got it earlier. And what we are doing this time is both the ends of the string, since the string length is not increasing, we are checking the velocity along the string and we are saying that at both the ends the velocity along the string has to be same. If this is your string going whichever way due to whatever setup which has been made, it is going with V1, this is going with V2, this is theta 1, that is theta 2. So along the string the velocity which is V1 cos theta 1 must be equal to along the string velocity V2 cos theta 2, because this length, the string length has to be maintained, it has to remain the same. So it goes V1 cos theta 1, this goes V2 cos theta 2. Since the string length is same in the same time, then the value of V1 cos theta 1 must be equal to V2 cos theta 2. So along the string the components are same. 90-degree component has no effect on each other. So this along the string, V1 was luckily along the string itself, so we don't have to do any component for V1, and V2 was not along the string, V2 was this way. So V2 along the string became V2 cos theta. So the along the string component we have equated. So that's your preferred method. So I'll write it as method say A. It's a different type of question. So that is velocity of end points of a string along the string are equal. So these are the end points of a string and the velocities along the string are equal. So I'll do one more method in this and then we'll use the most preferred method, which is method A, I would say, to solve all these questions. So next method is, another method in this is you write a geometrical relation between variables, you use your variables and then use calculus to come to the relation between the velocities. So you make a figure where you can write the variables which are changing and not changing. Like if I make this right angle triangle and I call this length as say x2 as a variable, okay, not a constant, x2 as a variable. So and this height of the pulley from this ground, this height is not the length of this, okay, the height over here is a constant, say h, and this length of the string over here from there to there, that's the hypotenuse, is L. So after a certain time what happens? After a certain time what is happening is the string is going to come over here. So that's your string, new string position and all. So what we see is your x has reduced, x2 has reduced, your L has reduced, h has remained the same. So we can write a relation between x and L and h at any given instant. So at any random instance, initially here when the body was here or there or wherever, the relation between these variables, what are the variables? The distance of the body from this imaginary point, fixed point, the height of the string where it is touching the pulley from their point, and from the body to that point of the pulley. So those three creating a right angle triangle. So what's the relation between them? Relation is x2 square plus h square is equal to L square. That's a relation. What are the variables over here? h is same. When x2 varies, L varies. So we'll differentiate this. We'll differentiate with respect to time because x2 differentiated with respect to time is going to give you v2. So differentiation of this using chain rule will be 2x2 dx2 by dt. Now x is reducing, so what is happening, your dx itself is negative, your x is reducing, so you can write or leave it. As the sign comes, we'll explain. So suppose x2 was increasing, so suppose you think it was going that way. So this is as if you are writing it is going that way. Dx2 is always positive. So in a differentiation, when you write dx, be careful of thinking it as an increment, not as decreasing the value, as increasing the value. So here dx2 is increasing. So what we have changed our original question. The v2 was this way, we have changed it to that way. So that's your 2x2 dx2 by dt plus differentiation of this constant would be 0 is equal to 2l dl by dt. Now when x is increasing, L is increasing. Okay, in this particular case when they were going down, we should have written minus dx2 by dt, and L would have also decreased, that is minus dl by dt. So you have to have a hang of the diagram also, what is happening. It is not just independent equation. So you should know which one is increasing, which one is decreasing. On x2 decreasing, L is decreasing, so both are having the same sign. On x2 increasing, L is increasing. So what we have over here is dx2 by dt can be written as v2 because that was the velocity. So that is dx2 by dt is your minus v2 in fact. So minus v2 I'll write, so don't bother about the minus sign right now. So it is 2x2 and then 2l, 2 I should have cancelled, dl by dt. So dl by dt, what do you think is dl by dt? dl is the increase in L, that's your dl. So the string which is getting stretched, when the body is coming here, the string is getting increased. So the amount the string is getting increased this side, the string which is getting pulled this side, that much must be the string which is going up. So dl is in fact how much it went up also. So your dl by dt is the velocity upwards. So since this velocity is marked downwards v2, v1, I'll write it as minus v1. Okay. Otherwise you could have taken v2 positive that side. So this would have been plus v2 and v1 positive that side. So it should have been plus v1. So this is minus v1 because I had taken v1 initially downwards. Okay. So what do we get over here? What do we get over here? What is the relation between v2 and v1? We get v1 is equal to 2 gets cancelled, x2 by L v2. That is what we get at any given instance. So at this particular instance, depends where we are talking. If x2 was here, the velocity ratio would be something else, and if x2 was this short, the velocity ratio will be something else as discussed earlier. If the x2 was this far off, then the velocity ratio will be almost 1:1 as discussed earlier. So which you can see, if this far off, then x2 is almost equal to the L length, and x2 is almost equal. So x2 by L is 1:1. So x2 is the base of this triangle, L is the hypotenuse. So at that instant it is the cos theta. So x2 by L is cos theta. So we get cos theta times v2. So again we get the same relation what we had got earlier. v1 is equal to v2 cos theta. So this is also a safe method to do. So I'll mention it as method B. So that is your method B. Write the relation between variables. You have to make up some variables and write the relation such that when you differentiate, you have to differentiate that with respect to time, such that when you differentiate the variables, you get the velocities what you were looking for. So these two methods and all those methods on top, everything applied, I think you can solve each and every question. So the preferred method I think is velocity along the string is the easiest to do. So try this with both the methods, and you see carefully I've taken different heights over here so that when you apply, you are applying different heights, which doesn't matter. So you are understanding the fact. So I know most of you are going to do by one method and not the other method, but just for practice sake, I'll request you to do both the methods. So I'll give you 2 minutes. I hope you are done with it. So method 1, method A, what is it? Velocity along the string of this end will be V1 cos theta 1. Velocity along the string will be, this angle was theta, so that is vertically opposite angle theta 2. So V2 is that way, along the string will be V2 cos theta 2. Along the string, velocity means how much string you are giving and how much string this is pulling. So what is given is pulled. So V1 cos theta 1 is equal to V2 cos theta 2 is the relation between them. So that is how it works. If I ask you that which will be higher, which will be lower, then the thing is that this velocity will be much higher than this velocity, because this is at a steeper angle. At a steeper angle, you require high velocity to bring about a change. At a flatter angle, you require even the lower velocity is going to bring as much of a change. So this will be the lower velocity in this case. If theta 1 is greater than theta 2, then V1 will be greater than V2. That is your analysis. Is this equation satisfying the analysis? Check for yourself. So what's the other way? Method B for the same question. Method B for the same question would be, method B was write a relation. So I'll write a relation over here. So I'll call this length as x1, height as h1, which is a constant, and this length as L1, which is varying. So I'll write x1 square plus h1 square is equal to L1 square. I'll differentiate this. This is 0. The differentiation of this is 0. You get a 2x1 dx1 by dt over here, and you get 2L1 dL1 by dt over there. Both are decreasing. You have a minus on both of them. dx1 is a negative, dl1 is a negative, so that cancels and become positive. So again, what we get over here is your dl1 by dt, sorry, dx1 by dt was your v1. So v1 is equal to L1 by x1 into dl1 by dt is how much is the string released by. So dl1 by dt. So I'll rather write it as x1 by L1 so that I get in the same format. Okay, and for this string, again you can take some height as h2 height, this length as x2 length, and that L as L2, and what we get is x2 square plus h2 square is equal to L2 square. On differentiating, you get 2x2 dx2 by dt. This time x is increasing, so it is plus only, is equal to 2L2 dl2 by dt. Your dl was what was decreasing over here, and here your dl2, your dl1 was what was decreasing, dl2 is what is increasing. In fact, dl1 is equal to dl2. This gone down, so it is a minus dl1 that way. So minus dl1 is a positive value. dl1 means this way. This means your dl1, and that's your dl2. dl2 is increasing. So always we think of incrementing variables. So what we get over here is v2, dx2 by dt is v2, x2 by L2 is equal to dl2 by dt. So dl2 by dt is the velocity of the string here. dl1 by dt was the velocity of the string there. So that velocities were same. So we can equate this equation and this equation, because this and this is same. So what we get over here is x1 by L1, v1 is equal to x2 by L2, v2. x1 by L1 is cos theta 1. So we get cos theta 1, v1 is equal to cos theta 2, v2. Cos theta 2, v2. Okay. So no need to do so much. A1 is what will give you the answer in one go. So method A. Now this one. When the rod is slipping, so this end is going down, going forward with velocity v1, and this part is going down with velocity v2. Now before you do the question, can you give me an idea in this particular stage when theta is greater than 45 degrees? then is V1 more or V2 more? So think on that, analyze. Don't calculate, analyze, and then you do and see whether your calculation supports your analysis or not. Okay, so what I guess again is a big movement over here is going to give a small movement over there. At 45-degree angles, since it is symmetric, then the movement here should have been the movement over there. So at 45 degrees, somehow, when I put theta as 45 degrees, my V1 should come equal to V2 in my resultant answer. So at least that much I should get in my resultant answer. If I get, say, V1 is equal to cos theta times V2, I am wrong, because at 45 degrees, it will say V1 is equal to 1 by root 2 V2, which is wrong. So I've already analyzed that at 45 degrees, this and this velocity should be same due to the symmetry of the situation. Once I do such analysis, I go ahead with my question. So again, we'll use method A, which is along the string. So this was going along the rod. So this angle is theta. V was the horizontal velocity. So along this, the velocity is V1 cos theta, and here this is going down, and the angle here is phi, which is 90 minus theta. So the velocity along the rod was equal to V2 cos phi, means V2 90 minus theta, which is equal to V2 sin theta. So now this rod is not shrinking, the rod is not getting compressed, so the velocity along the rod and the velocity along the rod over here must be same, so that these 2 points maintain the distance along the rod. So while they are going down, the distance is maintained along the rod. So V2 sin theta is equal to V1 cos theta. So what do we get? We get V1 cos theta is equal to V2 sin theta, and at 45 degree cos theta is equal to sin theta, so V1 comes equal to V2, so I am satisfied. So to write this answer in a better way, I get V1 is equal to V2 tan theta. So you may use method 2 also. I'll show you method 2. Not that long, in fact. You can use it. It is okay to be used over here. So say this length was y, this length was x, and the length of the rod was, say, L. So what do we have? At any given instance, x square plus y square, where x and y is variable, is equal to the L square. Length of the rod is constant this time, so L is constant. So on differentiating, you get 2x dx by dt plus 2y dy by dt is equal to a 0. Mind you, your dx is increasing, your dy is decreasing. So this dy in fact is negative over here. So minus dy is what is the positive thing over there. So if you write dy by dt, it means so much going up. So it is a minus v2, by the way. This thing is a minus v2 over here, because v2 is downwards. Dy by dt, without knowing the situation and all this, means dy means increment in y, increase in y. That means the maths assume that y is also increasing. It doesn't know that we are doing a rubber band or whatever. So dy is an increase for maths, and dx is also an increase for maths. So dy by dt is your velocity upwards, but v2 is the velocity downwards. So I'll replace this with a minus v2. So what do I get over here? 2 and 2 cancels, I'll not write that 2. X is x, and dx by dt, x was increasing and v1 was also going that way, the same way, which increases x, so not a problem over here. So we'll write v1 over here, and this one is y. 2 I've cancelled. Dy by dt I'll write as minus v2 is equal to 0. So what do I get over here? I get v1 is equal to y by x v2 for that given length y and x at a certain instance. So what is y by x? Y by x is tan theta for sure. So we get the same answer. V1 is equal to V2 tan theta. By both methods, not long. This is also quite short. Okay, and gives you a good analysis of the dy's and dx's and your calculus, a good hold on your calculus. So you may practice this also at times, but obviously for the exam, this would be the shortest if can be applied. So I think we'll do another type now. There are several questions where I can give you at an angle. Practice. If you have doubt, ask me in the class. So I'll give you another kind where a rigid body is on top of another rigid body. So what they call as wedge constraints. So I'll make some wedge and some constraints on that. In the meantime, just reflect back on what you have done. Do a practice question for yourself. Yeah, okay, do this. This is a very common one. People keep asking. It is there in various assignments. So here, if both these bodies are going down with the same velocity u and u, then this would be going up with how much velocity? So this v will be equal to how much? And it's given that the angle over here is same, theta and theta. So what you need to see over here is that this body is going to go absolutely vertically up because the angles are same, the velocities are same. Due to the symmetry, it will be going up. So these are all vertical lines. It is not coming vertically, just for your information. So it is similar to one of the questions already over there. So try it yourself. And in case one was double the velocity of the other, say this is u and that is 2u, then what is going to happen? What is going to happen is it is going to get pulled on that side more. So the velocity will not be vertical. And if you can find the velocity in that case, very good. So now let's see at this new kind of question. It's slightly different from what we have done earlier. No pulleys over here, no strings over here, so no strings attached. Now, if I move the block that way, or it goes that way, if the block goes that way, then this green block is going to come down. And conversely, if I push this block this way, then the green block is going to go up. Now what happens naturally is not the question over here. The constraints are the question. If this remains in contact with the other thing while it is being pushed, or while this goes down and that goes away, these two are going to remain in contact, then what is the relation of the bodies? So let me call this body as, this is body B over here in green, and the purple one is your body A. So what we have over here is, say the velocity or the displacement of this body is, say, we'll work with velocity. Velocity is VA. And this velocity will be downwards with VB. And surely they are constrained. Their movement is not independent. If this moves by, say, X and this moves by Y, then the movement is constrained. Now, how much will it be? You can make a diagram, you can make this go in and see how much it goes up, and note any one point on the body and see what happens to that point, where it is and where the other guy is. So in fact, I'll make that first so that you have a good idea of what is happening. So say the block has shifted forward and is here now. So this point would have shifted an equal amount. So I'll draw this here. And that's the new position of the wedge. The dotted position is the new position of the wedge. It has gone forward by X. Any one point over here, maybe this point, that has also gone forward by X, and it is here now. At the same height, the points are same. So this point is here now. So call this point as point P, then that's your new position of P. Similarly, this block I'll redraw. It would have come down. It would have come down vertically, and it would be over here. So say it has come down by Y. So this amount, what it has come down is Y. So what we see over here is we have a triangle formed. I'll draw in a different pen. So we have a triangle formed over there. You can watch over there, that's your Y, that's your X. So, and obviously this was along the incline. So this was along the incline. So this angle was your theta. That was the angle of the incline. So what is theta over here? In this diagram, this is your theta. So we have a relation between X and Y. What is the relation between X and Y? Clearly tan theta is equal to Y by X over here. So what we say is, Y will be equal to X tan theta. So if this moves by X, this is going to come down with Y equal to X tan theta. So that is solved. Now there are a number of ways of doing it, as I've listed so many methods. So one is drawing. I'm drawing so that you understand how it is happening, what is happening. You need not draw all the time. So this is what has happened. Now what you can do is, to solve such questions, you can again use work done by internal force is 0. Now what is the internal force over here? If these two bodies are taken, then the normal reaction on this and the normal reaction on that, N and N. So how much ever this point, or how much ever the work is done by this force, so is equal to the work done by that normal reaction in the other way. So net work done would be 0. So how do we solve it? I'll just draw this part over here. That's your normal reaction, that's your point, and that's your plane. We say the body has gone forward by X amount. So if it has gone forward by X amount, how much it has gone in the direction of N? So we have to do a N dot X to get the work done by N. So how much it has gone in the direction of N? So in the direction of N, this angle was your theta. So this angle over here is your 90 minus theta. So this angle again becomes theta. So this angle is again 90 minus theta. So N cos 90 minus theta is the N in direction of X, or X cos 90 minus theta is in the direction of N. So it is X sin theta, which is in the direction of N. So what we get is that the work done by this normal reaction is N X sin theta. Now for this body, that's the body, that's the point, that's the normal reaction, and we are saying that the body is going down by say Y amount. Now again, let us get the angles clear, and how much is the Y in the direction of N. So basically let me get this angle for you. How much is that angle? So before writing the angle, let us have it over here. This angle is theta. This angle is 90 minus theta. This angle is 90 degree. You have theta. So this is a right angle triangle. That's your 90 minus theta. This is your 90 degree. So this angle must be equal to theta. So anyways, that's a general knowledge. If you have theta with the horizontal, then the normal makes theta with the vertical. Remember that. If the horizontal makes theta with the incline, then the normal to the incline makes theta with the normal to the horizontal, which is the vertical. So if a wedge is inclined at theta to ground, then the normal to the wedge will be inclined to theta to the vertical. Okay, so what do we have? How much is the movement? So the Y along N is Y cos 180 minus theta, but you have done in trigonometry, that is minus cos theta. So we can say that it is minus Y up and cos theta along N. So it is minus Y cos theta along N. So the work done is minus N Y cos theta. The total work done will be 0. By those two forces, the work done will be equal and negate each other. Total will be 0. So what we have is N gets cancelled because it is action reaction force. This normal reaction on the two bodies are equal and opposite by the third law. So same as we were doing in method 3 over there. So what we get? Is X sin theta is equal to Y cos theta. So your X or Y, what were we finding earlier? Y. So what we get is Y is equal to X sin theta by cos theta, which is your tan theta. Same as the answer earlier. You might think that the drawing was easier, so then you can go with the drawing. At times you feel this, if you are too much into work done and all, which is the chapter after your laws of motion, so you might be inclined to do through work. So work done by the N on this body and that body, you can take it as equal and opposite because N and N are internal forces. So work done totally by them has to be 0. So we can use that. So more details on the normal reaction and everything I will be doing when we do, and we can have a better explanation of this when we do laws of motion. So here, just for the constraint sake, any other way would you like to do? That is, it's a sort of, again, if I do a variation of method 2 over there, it will be a sort of the diagram again what we are drawing. So diagram is pretty safe to go with. Now you're cross checking. If you want to cross check whether you have got it right or wrong, then yeah, that's a good idea. And you can cross check with various angles. See, if the angle was very shallow, if the angle was very shallow, then what happens? If you move the wedge, maybe whichever side, if you move the wedge that side, it is hardly going to go down. So your y is almost equal to 0 if theta is almost equal to 0 is what we are seeing. So is that right? Yes, when we put tan theta, theta is 0, y is almost equal to 0. So at least that is coming all right. And suppose you had a very high angle, very high angle, that's your wedge, very high angle, that's your theta, and that's the object on the wedge. So what happens over here, if I move by x, if I move by a little x, what is going to happen? It is also almost going to fall down a lot of distance. So if it is totally vertical, just 1 degree, if I move a very little amount, it is going to go down a large amount. So that means if x is very small, still y will be very high, if angle is very high, if angle is almost 90 degrees. So is that true over there? X is very small, but tan theta is almost 90. So tan at 90 is almost infinity because it becomes sine by sine 90 by cos 90. Cos is almost 0, so it becomes almost infinity. So this y becomes almost infinity, which is the case what we are seeing over here. It becomes a very large value even if x is 0.00001 millimeters and this is tending to 90 degree. It is just short of 90 degree, 90 minus. Then still your y will be a very large y because tan theta will be almost infinity. So it is almost verifying, and at 45 degrees we can imagine, like if the wedge is 45 degrees, then the movement by this and the movement by this is, by intuition, it has to be same. So that is how you verify your formula. It is best to verify once. Suppose by mistake you got cot theta, then you will get cot when you are verifying using this method. So very similar setup would be, it is the same setup in fact, drawn in a different way. They make wall on two sides instead of this wall, they have made this wall, and you'll have an object which can slide down, object which can slide down on another object where the inclines are matching, same as this part where the inclines are matching. So it's the same thing, it comes down and it goes away. So answer will also be the same. In the same case, you can draw and check, you can do normal reaction here and here, say that this movement of this thing is y, find out the force, say the movement of this thing is x, find out the work, not the force, find out the work by this normal reaction, with this y, find out the work by this normal reaction, n and y in that component, so n dot y you do and n dot x you do, and should be equal to 0. So you'll get what we got over there, that equation. So let me give you something which is having pulleys also and angles also, and let's see what you do about it. So that's our next question. Here we have a pulley also and there's a wedge on which there's a body. So both kinds of constraints are over here, and we have to find if the body B moves by a certain amount, say x, then where will body A move and how much? Now if B is moving this way, it is going to swing down a bit and it is going to go somewhere over here. So we have to find exactly how it is going and how much, with what velocity. If the velocity was v, then what is the velocity of that? So it has moved dx, then what will be the d displacement of the body A? That is what we are going to do. It is clearly a constraint. This body cannot pierce into the wedge. That is one constraint. The rope is going to be tight always. That is another constraint. So with whatever force we are moving this body, with whatever force, with itself normal reactions and all is moving, or we are assisting it by putting some force, if a certain distance x is moved, it is going to move a particular distance y. It is not going to be a force dependent thing. So it's a constrained, it is a constrained motion between A and B. It is independent of how much force we put. The displacement of this and displacement of A is constrained. So first we have to figure that in our mind. So it's a constraint or not. Yes, it is a constraint. And every time we move an inch this side B, A is going to go to a particular position only all the time. So like this and the one before, we can discuss everything in terms of work. But I would rather ask you to make the diagrams and get the actual positions, how it is going, so that you have a better idea of what is happening, and then we will deal this in two different ways. So since I'm going to deal it in two different ways, let me make another diagram over here for this. That's your angle theta. There's a pulley on it, and then there's a body A attached to the string. That's your ground. Okay. So if this big mass, if this body B goes here by x, it is somewhere over here, then again I am going to draw the same diagram. This would have moved by x, this point has moved by x, and this is the new position. That's the new position, and that's your pulley. So pulley would have come over here somewhere. So that's the new position. So this part of the string remains as it was. Rest will bend, and it is going to go in here like this, and the body will be somewhere over here. Now we have to get how much is the movement and what is the direction of the movement. So we'll use vectors to do it. What we'll try is using the vectors. So say the velocity of B this way is VB, that is with respect to ground. So that is velocity B with respect to ground is this way. Now velocity of A, that's your A, body A, velocity of A with respect to the body B. What do you think will be the direction? With respect to body B, with respect to body B. So that's the key over here. With respect to body B. Meaning to say that body B is not moving. How does body B perceive everything happening? So actually the body B had gone to the wall. But for body B, what is happening? If you are on body B, what do you feel? You feel the wall is coming towards you. The wall has come towards you so much. So for body B, the wall has come in. The wall, you have moved x. Body B feels as if the wall has come in by x. So if the wall comes in by x, if it comes in by x, what happens? It's this one A is going to slide down on body B by x. So A is going to slide down on body B by x, if that's the velocity of body A with respect to B. So if B was going with VB with respect to ground that way, that was your x, what I'm saying, then the body feels that the wall is coming towards the wedge with a velocity of the same thing, B with respect to ground, and that is how much this body is going to go down along the slide. So if I have a mark on the slide, say I'll put an orange mark. So if this other edge this is a mark on the body. So later on the body A will be somewhere x, if it has gone x forward, it will be x down. It will be x down, and the position of the body will be something like this. So try to understand this. With respect to the body, it would have come over here. So the body would have come over here, and this distance would also be x. But the wedge itself has gone forward. Whatever this point was P earlier and this point was Q, those are the points on the wedges. On the wedge, that was your P and that is your Q somewhere. So there is where your P is. I've drawn the thread a little less. It is that much more. So P has come over here. That's your P. And Q has come over here. That's your Q. And the body is here. Finally, the body is here. Okay, so this diagram is clear. I'll make it over there further. So what we see is this string has increased by x length. this part of the string has decreased by x length, this part of the string has increased by x length. It has gone down, and this has gone down along the wedge with a distance by a distance of x. So it is pretty easy now. What we have to find is velocity of A with respect to ground. What we know is velocity of A with respect to B and velocity of B with respect to ground. So I hope you remember how to connect these vectors. Velocity of A with respect to ground would be equal to velocity of A with respect to B plus velocity of B with respect to ground. So I'm doing it deliberately in the vector way because we have done this a lot earlier. So I just want to make use of that equation. You have done a lot of study with this equation, so we'll use it. So we know velocity of A with respect to B, velocity of B with respect to ground. So what is velocity of A with respect to ground? So we'll draw the vectors. What is the velocity of A with respect to B? It's a vector which is along the slide. So I hope I make it almost parallel. So that's your velocity of A with respect to B. This angle is exactly along the slide because A with respect to B is along the slide. With respect to B, A was just going down the slide as if B is not moving. So this vector has an angle of exactly theta with the horizontal. Okay. Plus velocity of B with respect to ground. So velocity of B with respect to ground is horizontal. Now what's the magnitude? Fortunately, the magnitude of both of them are same. We have discussed that. So A with respect to B would have gone down by x, and B with respect to ground has gone by x. So the magnitude of velocity of B with respect to ground, magnitude is equal to velocity of A with respect to the body B. So these two magnitudes are same. Both were x and x in a given time. So this will fall short of the vertical. This will exceed. So here it's an isosceles triangle. So the resultant direction is this. It is bound to be backwards. No matter what, it is going to swing back. It is going to come back. So maybe this is not a very clear depiction. It comes back a bit. It comes back. Why it comes back? Because this line is going to exceed this line. This was at an angle and this is horizontal. So what we see is this body is bound to be back. By this constraint, it is bound to go back. Why? Because this x is equal to that x. That is what we have seen. If it goes by x, then this goes down by x. But if the body has moved by x, if the body has moved by this x, this point, this A has gone down by x, but the body has moved back by x, this x is going to exceed that line vertically and it is bound to come back. Now with forces, we may analyze it later on. You have for the body A, you have a normal reaction acting on it, you have tension acting on it, and you have mg which is down. And if I have to just consider the back and forward thing, you'll have a tension component in the front, and you'll have a tension component, and you'll have a normal reaction component at the back. What we can safely say is tension component in the front will always be greater than normal reaction at the back. When we do forces, we'll analyze that. For now, just come back to this situation. So what we have done is we have used our vectors concept. We have figured out the velocity of one with respect, we have given velocity of the wedge with respect to the ground, figured out the velocity of A with respect to the wedge because that was easier to figure out in this case, and we have got the actual velocity of A with respect to ground. So now how to calculate this? The calculation is pretty simple. This angle is theta because this VAB was along the incline. So fortunately it's the same angle, theta. So just on this triangle we can use vector formula, or we can just get the horizontals and verticals. So this vertical is x sine theta. This horizontal part, this small horizontal part is x minus x cos theta, because this much is x cos theta. This totally was x. So you have x minus x cos theta. Hence that orange line, the displacement of that is going to be, the displacement of A with respect to ground is going to be x sine theta square plus x common 1 minus cos theta whole square whole under root. So if you work on that, you'll get x squares, which is outside the root, so becomes x. Sine square theta plus, we have a sine square theta from here, cos square theta from there, that gives you a 1. Then we have a 1 from here, that gives you another 1, so you'll get a 2. And then you have a minus 2 cos theta over there, so minus 2 cos theta over there. So if you want, you can further work it out. I'll just quickly do it for you. 1 minus cos theta. You have done enough trigonometry. Trigonometry is what is going on. So what do you think is 1 minus cos theta? Can I write it in a compact way? Yes, we can use cos 2 theta formula as 1 minus 2 sine square theta. So what we get is 1 minus 2 cos theta is 2 sine square theta. So this is going to be 1 minus cos 2 theta. So this is going to be 2 is already there, then another 2 sine square theta by 2. So I'm just doing this because many a times you'll find that this kind of format gets reduced, and what you ultimately get is your XAG, this part is going to be x times 2, and 2 is outside. I'll put a 2 first. 2x sine theta by 2. So that is your answer. That's your blue line in the clear over here. The movement will be 2 times x sine theta by 2. So that's your displacement, and the angle is, as you can see, the angle will be given by this diagram. So the angle, say, if you want to know the angle with the horizontal, call it as phi, and that angle phi will be given by tan phi is equal to sine theta upon 1 minus cos theta. Again, in the reduced format, you'll have it in half angle. Sine theta, you can write it as 2 sine theta cos theta, and that one in sine square theta by 2, and one of the sine theta by 2 will get cancelled. So I'm not going into that. So the thing is, this is your final answer. And again, I'll emphasize what we use over here is the movement of A with respect to the wedge. And how did we find out that? We were keeping the wedge stationary, and instead of moving the wedge to the wall, we moved the wall to the wedge. We moved the wall to the wedge, and we can easily see that this would slide down. If the wall moves by x, this will slide down by x. So that was a key to find the answer over here. And a nice diagram with your angles, correct angles. This angle was your theta, so you did the vector. This was your x, and x is what is the key thing you figured out, angle theta. So finding this is not a big deal. You can apply cos rule over there to get that, and still you'll get the answer. What's the cos rule? The angle, the side over there, XAG, is equal to under root of x square plus x square minus 2x square, the sandwiched angle. The sandwiched angle is theta over there. So that's a square plus b square minus 2ab cos theta. So that's the same thing what we did over there. So this is by the Pythagoras theorem, this is by the cos rule, which is all the same. Okay, I'll give you one question, that is going to be your last question, where you have wedge on wedge and pulley also, and maybe a movable pulley. So a movable pulley and a wedge on wedge. So that is like the ultimate question in these kind. Okay, so hopefully you get that, and that would be the end for this lecture today. So these two are the questions. B and A are movable. This pulley is fixed to B. Same situation over here, but in the first situation, rope is going around, and back to this it is attached. Here it is attached straight away. So what you need to get is, when B is moved by X, where and how does A move with respect to B and with respect to ground. You have to get the displacement of A with respect to B as well as displacement of A with respect to ground. When B is moved by X, when your displacement of B with respect to ground is equal to X. So this one. Okay, so same thing over here. You have to find the same thing over here. And just to give you a hint, if you to know whether you are going in the right track or not, one of the answers of the two, I'll not tell you which one, comes, I guess, under root 5 plus 4 cos theta as a net displacement. If you have moved by x, you have to get the directions also. And one more thing, to verify your answer, you can take extreme conditions, but then you'll run into some confusion. Like the previous or previous to previous question, what I have done, you had answers which was something like 2x sine theta by 2. Now try to see the extreme conditions. When theta is 0, then the movement of body A and B will be how much? Does this satisfy that or not? When theta is 90 degree, when the wedge was vertical, then when theta is 90 degree, is this answer going to come right or not? It is, by the way, in that question, it is not going to come right. Sine of 90 degree by 2 is sine 45, involves a root 2, and nowhere you'll have a root 2 in the actual situation. So why is this answer giving you a root 2? Think over that. So when you apply extreme conditions to theta to check out whether your answer is right or not, you have to keep your mind open whether all the constraints what you were thinking for normal thetas, which is between 0 to 90, some angle theta, those constraints will apply when you're taking the extreme condition or not. Those constraints do apply or not. So one of the unset constraint is the body A lying on body B. Body A is always touching body B. So body A, if the body B goes in, body A goes in with body B. So there where it fails, I'll just give you the answer to it. When body B goes in, body A, according to the equations of math, has to go in with body B, which is not physically happening. In physics, what is happening is it is just going to go down, it is going to leave the contact of body B. So there it may fail. Okay. So do these two questions. If you get them right, then we are all set. You have learned constrained motions very well. Thank you. Goodbye.